seconds. Okay, I'm returning to the meeting now. And I'm going back to there. Okay, you see my blackboard now, is that right?
Yes, sir.
Okay. Now, we've still got 10 people here. 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. Okay, nobody new has come in. So I'm going to move this thing down to the bottom. You can't see it, but it's just in my way. All right, this is what y'all see on Blackboard, right? Now, let me just get a few questions. Are all of you Lawson students, or are any of you transient students?
Lawson.
Everybody's Lawson. I thought you probably would be, okay? So you're familiar with Blackboard Ultra, right?
Yes, sir.
Okay, well then this will go hopefully a little faster. Y'all all saw the announcement, obviously, about the Zoom because you got here, right? And that's where your Zooms will be every time under announcements. Okay, when you pull it up, it'll pop up there. Okay, also under Blackboard, you will see the syllabus. Now this is under content of part of Blackboard. So that's what we're going to do now is start with the syllabus. Before we do that, does anyone have any general questions, overall questions, things you want to get squared away before I start talking, you forget about them? Everybody okay? All right. So let's start with the syllabus then. Okay. When you click on that, you get this. Well, you can't click on that. Nothing happens. You have to go over here to the 3 dots, but y'all know this. But I'm used to having transient students, so I'm showing them how to use this new Ultra. And then you download the original file, and it takes just a few seconds, and then you can click on it in the corner. Okay? And here comes the syllabus in its gory detail. All right. There we have it. Can y'all see? Oh, the screen sharing's paused. Let me get the new share here and show the syllabus. Let me know when I get talking about something and you can't see what I'm talking about. Okay, there it is. We are Physical Science 111, Physical Science 111, Physical Science 1. It's a 4-credit hour course. Of course, we'll meet for more than 4 hours because this is summer term. We're on a compressed schedule. So we meet for however many hours it is from 2:30 until 4:45. That's 2¼ hours a day for 2 days a week. So that adds up to more than 4 hours. 3 credit hours, theory credit hours, and 1 lab credit hour. Well, the lab is 2 1½ hours a week. So it's normally a 2 lab contact hours for every 1 hour credit. You have 3 contact hours for every 1 hour credit, though we may not be a full 3 hours every hour and a half every time. So you get 5 contact hours, which is actually more than that. That would be in a normal term. We do meet on Mondays and Wednesdays. Monday and Wednesday, both from 2:30 to 4:45 is the class time, and 4:45 to 6:15 is the lab time. And again, we may not take the full hour and a half for labs every time, but that's what we're allowed. There are no campuses, so it's all virtual. No room numbers. You're whatever room you're in. I'm in whatever room I'm in. I'm in a spare bedroom up here. My wife moved me as far away from her office as she could, so I won't be bothered by my live talk. My name is Charles Fowler, as I have most of you. My office is not here. We're off campus, so no office phone. We're off campus. However, I do have email. And I will be trying to check email every day. Sometimes it'll get really bogged down, but I'll try to catch up then on other days. So hang with me. I'm a bit slow with email. Here are my rough office hours. And I say rough because later I'll show you my locator card, and that will illustrate what these office hours are. So basically on Mondays and Wednesdays, I'm in the office in this bedroom up here from 8 till 11:30. At 11:30, I have a calculus class that begins at 11:30 and goes till 2:25. And then at 2:25, I have a full 5 minutes to get rid of those books, get in my new books, get everything set up. It's not enough time. So I'll almost always, unless I can let them go a little early, I may be just a little late getting here just because 5 minutes is not time enough to do all the changes I need to make. So anyway, that's it. And then this class goes to 6:15. After that, I'm through for the day. I'm really through for the day. Okay. On Tuesdays and Thursdays, I have morning and afternoon classes. So I have office hours from 8 to 8:30 in the morning on Tuesday and Thursday. And then starting at 8:30, I have a differential equations class. At 11 o'clock, I've got a linear algebra class. It gets through at 1:15. So from 1:15 until 5, I have office hours again on Tuesday and Thursday. But then at 5 o'clock, I have a physics class that goes until 6:30. So after 6:30, I'm done. Okay. On Friday, the college is closed, so we are not necessarily available at all. We'll periodically be checking emails, but not on a regular basis. My wife has a honey-do list about 1.5 miles long, and that's what I'll be doing on Fridays. Valerie is laughing. I can see she makes them out too. Okay. All right. Okay. So that's where I'll be during the week. Again, I'll show you my locator card later, and that will explain this a little bit better. Now, the course description is pretty simple. We didn't make this up. This is done by the state, and they decide what we teach, and they work with the four-year schools, and if we do this, they give you credit for it. So this course provides a non-technical student with an introduction to the basic principles of geology, oceanography, meteorology, and astronomy. The laboratory is required. Okay, I've got someone coming in. Oh, Parisha must have had to leave and come back. So I already had her here, so we're still should be sitting at, well, she's not here yet, but that'll be 11 because I'm the 11th one, okay? Now, we're going to cover each of those areas not equally. Here's how we're going to do it. We're going to start with the astronomy, 3 chapters on astronomy. Then we'll go to geology and earth sciences, and there's something like 4 or more chapters in that. Then we'll do meteorology or weather and climate, 1 chapter there, and then oceanography is the last chapter, and that will be at the end. Well, I couldn't change this. This is how they wrote it up. I teach it the way the book presents it. Okay? Prerequisites, basically there are none. It says as required by the program, whatever program you're in. Okay, we got someone else. Capri must have had to leave, and she's coming back. So we're still at how many? 11, so that will be 10. Unless someone new has come in. If someone new comes in, please say something so I can get you marked on the roll. All right, the textbook, I'll show you what it looks like. If you get one, it looks something like that. Can you see that in my camera? Can you? You can't. Where you were seeing me.
Is that the same one as the 112?
Okay. When you were in 112, did you have a little thin book or a thick book like this?
I think it was both.
Oh, you had both. If you have the thick book, it's in that book. If you had the little thin book, that was a custom text that contained only the chapters that 112 used, which were chapters 1, 2, 3, 4, 6, and 8. This book, if you have the big book, it has something like 24 chapters in it. Yeah, all of them are in that one, okay? But if you have the little thin 111 book, it has just the chapters we're going to be covering. I'll hit those now. 14, 15, and 16. Those are the 3 chapters on astronomy. 17, 18, 19, and 20. Those are the 4 chapters on geology and earth science. Then we skip 21, 22, 23 is the chapter on weather, and 24 is the chapter on oceans, Earth's waters. So those are the 9 chapters we'll try to cover in this class. So if you have a book that has those chapters in it, 14, 15, 16, 17, 18, 19, 20, 23, and 24, that's our book. Okay? If, however, you have the other one that only has chapters 1, 2, 3, 4, 6, and 8, that was 112. That will only work for 112. Okay? So you'll need to get the other book. You can contact the bookstore. I bet you there's some email address. I'm guessing it's something like bookstore@lawsonstate.edu or something like that. You'll probably be able to get in touch with them. If not, try to get in touch with the bookstore manager. His name is Mr. Dan Fitz. So Dan Fitz, Fitts, or dfitz@lawsonstate.edu. That would work too. It's dfitts@lawsonstate.edu. And see, because he had some of these books probably in the bookstore, and he can probably arrange to either mail it to you, ship it to you. We'll talk about that in just a little bit. Okay, in fact, that's the very next thing here. What I was talking about before, though, was the prerequisites. If you've had at least Math 098, or you scored for Math 100 or higher, you're okay for this course. We'll be doing a few things that might be a little beyond that, but it's not going to be much, and I'll explain any higher math that you might need. So if you have finished 098 or something about like that, or even are in 098, that'll probably be sufficient. Okay? Now let's get to the textbook. We were just talking about it. That was a picture of it. The author is Bill Tillery. Now some of those smaller texts will have my name on the front, not his. I didn't write the book. I just gave them the chapters that we wanted to do. So if you have one of those, it'll say somewhere on there PHS111. If yours says PHS112, wrong book. Get the correct book. Okay? And the bookstore had some of those. I assume they still have some, and maybe y'all can make arrangements with Mr. Fitz of how you can get a copy of that book. But it's a McGraw-Hill book. So if you go to McGraw-Hill's website, let's see where McGraw-Hill is. Yeah, here's the symbol for McGraw-Hill. That McGraw-Hill Education is the name of it. It's the 11th edition. It's also on the front somewhere there.
Dr. Fowler, I have a question.
Yes.
Will our assignments be coming out that book, or will you be making those up?
Okay. Now, by assignments. The book has at the end of every chapter some excellent study materials. Okay? Now, if you have the book, or at least a virtual copy of the book or something like that, ebook, something like that, you can see those. Now, they're not necessary. That's not going to be necessarily what I call homework assignments. Okay? Those are just things to be done. Now, what we will be doing just about every day, maybe not today because we aren't going to be able to cover very much today, are labs. Now, the labs I'll either put on Blackboard, okay, and we'll get to that in just a little bit, how I'll do that, and or, in fact, all of them I'll probably do that way, but I'll show you how to do those in class during that lab period from, what is that time, 4:45 to 6:15. Those are the times we do the labs, and usually I'll put those out there for you. That's going to be most of what you have to turn in. When we finish a chapter, I'll be giving you a test, and we haven't gotten that far in the syllabus yet, but since it's come up now, let me go over that. How would you prefer your test, in class or take home? Anybody?
Take home.
Really?
Take home.
Oh my goodness, what a surprise. I was thinking y'all were going to all say in class. Wow. No, I'm just kidding. I figured y'all would want to do it, take home. Okay, so when we finish this chapter, I will send you the test, okay? It will either be a Word format or it'll be PDF, one or the other, okay? Some of them I have in Word format and some of them have in PDF. And I'll send that through Blackboard, and I'll show you where to get that. It's through Blackboard Messages. That's also where the labs will be coming. And when you send things back to me, you can either send them, okay, I'll go over this later, but since it's come up now, we'll do it. You can either, if you can and want to, type in your answers in Word and send it back to me that way. I had some students in the last class who did that. That's fine. More likely, you'll take either a PDF of it. You can do that with your cell phones or with a tablet, or you can do that if you have a scanner, either at work or at home. You can scan them and send it to me as a PDF. And you can send it either by email or through Blackboard messages. And we'll talk about that a little bit later too. Okay? Or you can take a picture of it with your telephone, with your smartphone, and that would be a picture file, either a JPEG or something like that, and send that to me. Now, when you're doing either scanning it with a phone or tablet or taking a picture with a phone or a tablet, try to get the light coming in obliquely from the side, so that when you're standing there taking your picture with your phone, you don't get a shadow where the phone is or where your arms are, because then I can't read what's in the shadow. So try to have the light coming in from the side, like a lamp over on the side, so you're not making a shadow on it. So get me the best that you can sending it to me. Okay? I'll be doing the same when I send you a PDF. I'll try to do that. My wife has a new iPad that does a real good job of taking PDF pictures and sending them. I'm not very good at it, but I'm getting a little better and more confident. But this morning we couldn't get one to work, so she's working on that sometime today. She's my IT person. Okay. So as far as the book goes, it's a great idea to have the book. I know that's probably what you were asking before, because nothing, I'll say this at the end of every chapter, I'll say it right now, nothing replaces reading the chapters. So if you can get your hands on some form of the book, a used book, a rented book, a bought book, a iBook, an ebook, whatever, if you can find this book and have it to read, that's going to help you in the class a lot.
Excuse me, I have a question.
What's that?
Can you upload the name of the book onto the Blackboard?
It's right there on my syllabus, right there. Can you see my syllabus on the screen?
Okay.
Okay, the textbook is...
Yeah, if it's on the syllabus, then I can just go look at it.
Right. Bill W. Tillery, Fiscal Science, 11th edition, Boston, Massachusetts, McGraw-Hill, copyright 2017. Now, if you need the ISBN, I can give you that right now. Do you want that? Do you need that?
Yep.
Yes?
I don't think so, long as I have the name of the book.
Okay. What I'll do, I'll hold the ISBN up here right in front of the camera if anyone does want to write it down. Can you see it? Do I need to go right, left, up, down, forward, back? Can anyone see that?
Put a little to the right.
A little to the right. This right?
My right. Yeah.
Okay.
Right there.
Right there.
Thank you.
All right. So, if you need that, there it is. Okay? Now, the reason I say the textbook, we're not going to do too many exercises from the book. Those who were in my 112 class, and that's only, I think, Capri maybe. Were any of the rest of you in it?
I was in Math 112.
Oh, Math 112. I'm talking about Fiscal Science 112.
Oh, no, sir.
Okay. In 112, there are lots of exercises, examples to do. This one has a few in the text, but they're not very useful. So we're not going to spend a lot of time with it. But a lot of the words, let me phrase it this way. When we started teaching physical science as opposed to physics, I was trained in physics. I did an undergraduate degree in physics. I did graduate work in physics, okay? That was fine with me, okay? But when we went, and we still teach physics, and I teach a physics class right this term. But when we went to physical science, that opened up into a lot more things than physics. Now, the first part of the book, there was chemistry. Well, I had a bunch of chemistry courses too. I had chemistry as an undergraduate. I had some graduate level chemistry courses. So I was okay there. Okay? But when we went to physical science, here we hit geology, for instance. Well, I took some graduate courses in geology and geophysical sciences, so I was okay with that. We did earth sciences. My master's and PhD were in earth sciences. Okay, so I'm fine with that. We did, however, this book has 3 chapters on astronomy. I've never taken an astronomy course in my life. So before I taught this physical science the first time, I took this book home with me. Actually, it was an earlier edition, several editions ago. And I read those chapters over and over and over to make sure I understood, because in one part of the chapter they'd be talking about one thing, and another part I thought they were talking about the same thing, but it was a little bit different. Okay, and then when we did the labs, it was a little bit different. So I read these chapters repeatedly. Now I feel really comfortable teaching it. That's why I say nothing replaces reading the chapters. Now, meteorology, never had a meteorology course in my life. I did have a course in crop science that dealt a little bit with meteorology, but not that much, okay? And then oceanography, never had an oceanography course in my life, but I have had, some courses that prepared me. So nothing replaces reading the text. So if you can get your paws on a text, find somebody that had it last term. If they are stuck with a book, they may give it to you or sell it to you really cheap. See if you can ask around and see anyone who's had the course before. If they still have a book, get one. They're used books, they're rented books, they're all fairly cheap. There's these places you can go. I can't think. There's one called Chegg or something like that, that you can rent books from or get used books. There's ways to find them. You can do it. If you can find an earlier edition, nothing much changes except the page numbers and the pictures, and very few of the pictures change. So, in fact, the PowerPoint I'll be using is from an earlier edition because I didn't have one from the new edition. They didn't send me one. It's the same. Nothing much has changed. So if you can get an earlier edition of the book, they'll probably be really cheap. Okay? So see if you can. The bookstore, those customized texts, they're not that expensive. So see if you can get a copy of the book. Now, I know that was probably more than you asked for, Cramisha, but it really would be beneficial to have a text in front of you. E-text or whatever. Okay. So let's go on. Blackboard. All courses, I don't want to read all this. You've probably seen it a dozen times. You've been in these. On my Blackboard, and that's what we're looking at now. We're looking at the syllabus on Blackboard. Handouts, things like my locator card, the research paper assignment, all that kind of stuff, you'll see those on Blackboard. Okay? PowerPoint shows. I'll show you where that is on Blackboard. Activities, I wish we had some. Normally in this course, we tried to go on 2 field trips. We can't do it now, not with COVID-19. Okay? So we'll try to find some labs that will take the place of those activities. Assignments, like I said, the research paper assignment is already out there. Now the other assignments, I know what the dean wants us to do is type something up in Blackboard every day and tell you what the assignments are. What I'm going to do, I'm recording this class. Can you see this little red circle over here in the lower left corner with a time clock going next to it? Do you see my cursor going around in circles here?
No.
You do see it?
No, sir.
Okay, you can't. I'm recording the class, okay? When the class is over, I'll upload this recording, which is everything that's projected on the screen, and everything I say will be recorded and saved to a YouTube video, okay? And that YouTube video, once it uploads, it takes about an hour or 2 to do that. When it gets uploaded, then I'll put it into a playlist, and then I'll show you on Blackboard how to access the playlist. So if you weren't there in class that day and you want to know what's due for the next day, go to the YouTube video and you'll see and hear everything there. Okay? Now,
will you also be posting it on the course calendar?
Okay, I don't know what you mean by course calendar. It will be in content, course content, same place I got this syllabus, that's where the YouTube playlist will be, the web link to the playlist will be. I'll go over that when we get there. We're doing that just a little bit later, okay? I'll show you how to find those, okay? They say announcements. So certainly the Zoom announcement will be there on Blackboard. So that will be there before every class. Usually I'll do it the evening before. For instance, as soon as this class is over with, when I shut down our Zoom here, I'll schedule my 3 classes for tomorrow. Okay? And when I finish the last class tomorrow evening, I'll schedule our Sunday school class for Zoom. So after Sunday school class is over on Sunday, I'll be scheduling the Zoom for Monday. So that's how we do. Okay. So here are the course student learning outcomes. They call them professional competencies and objectives and student learning outcomes. Students will demonstrate the knowledge of stars, galaxy, and the solar system. That's chapters 14, 15, and 16. I'll try to work up a lab. Now, this is the first time I've done this course virtually, so I've got a lot of work to do for this class to try to come up with labs. Most of the time we're in class sharing the devices to do the labs. We won't be in class. I can't share the device, so I'm going to try to find labs, virtual labs out there. I'm going to try to talk with the Birmingham Astronomical Society to see if they have some things that will help. I'm going to do whatever I can to try to make up some labs for us. Okay? I'm behind the 8 ball on it. I'd hoped to at least have the first one ready today, but we weren't going to have time for it. I'll be working on that this weekend, if my wife lets me anyway. Okay. So chapter 14 is on the universe. Chapter 15 is on the solar system. And chapter 16 is the Earth in space, basically the Earth-Moon system. Okay? And we'll have at least one lab with every chapter, and we'll have a test at the end of every chapter. Okay? We may have 2 labs in some chapters. We'll see. Okay? Students will demonstrate the knowledge of rocks and minerals, plate tectonics, and building and shaping of the Earth's surfaces. That's basically chapter 17 is rocks and minerals. Chapter 18 is plate tectonics. Chapter 19 is building the Earth's surface. And chapter 20 is shaping the Earth's surface. Those are the 4 chapters on geology and earth sciences. We'll have at least one lab with every chapter, and we'll have a test with every chapter. Okay? And so those will either be, the labs will either be whatever you call them, simulations, or they'll be whatever I can put together. Okay. Then chapter 20, the next item. Students will identify key indicators of weather and climate. That's chapter 23. We'll have one lab with chapter 23. I don't know exactly what it'll be yet, but I'll come up with something, and we'll have a test in chapter 23. And we'll have the 4th student learning outcome. Students will demonstrate knowledge of the Earth's waters. That's chapter 24. The lab assignment is already prepared for that one. That's one that you'll just do, and you will need a book or a resource for that. But now remember, labs are laboratory, okay? You're in lab groups. I'm not going to assign you to groups, but that means you can work with each other, okay? So if you want to get somebody in the class, share names, email addresses, whatever you want to share, and you work through these labs together, that's what labs are all about. They're working together. That's one of the objectives here, is that you work together with the labs. It's hard to do in a virtual environment, but my last class managed to do that pretty well. Everybody, students will write a library-based or internet-based research paper. We'll talk about that a little bit later, okay? And you'll work together, like I said, in groups to solve laboratory assignments, okay? We'll do it as a whole group, a big group, or we'll do it, you can do it in smaller groups. And then there will be a comprehensive final exam at the end, and that's what we required from everybody. Okay, so how will I go about evaluating or assessing how you've been doing? The research paper is required, not optional. Required for the class. It will count as a test score, and that test cannot be dropped. If you don't do the research paper, that's a 0. You don't want that. Do your research paper. We'll talk about that later. A chapter test will be given at the end of each chapter. That's 14, 15, 16, 17, 18, 19, 20, 23, and 24. That's, I think, a total of 9 tests in addition to the research paper. Your lowest one of those chapter tests can be dropped. Okay? The final exam, comprehensive, that cannot be dropped. That's what we use to measure your overall student learning. Okay? Let me tell you a secret. It'll probably be the easiest test you do. Most of the rest of them are going to be largely multiple choice, a few fill in the blanks, very few problems to do, though there might be a couple. But by and large, the final exam is matching. So it's really, really easy. So everybody will do that. Okay. Now, there will be at least one lab assignment for each chapter covered. Okay, we may have more than one on some chapters. The lowest lab assignment may be dropped. Okay, the laboratory grade will be averaged from the remaining laboratory assignments. Now, here's what I do. Okay, well, the laboratory average will count as 25% of the grade. Now, where did I come up with that? Well, think back earlier. Let me scroll up a little bit here. Okay, right here. You get 4 credit hours for the course. 3 of those credit hours are theory. In other words, textbook. Okay? 1 of those credit hours is for the lab. So 1 out of 4 is 1/4, 25%. Okay? So, with that in mind, that's where I get that your laboratory average will count as 25% of the final grade. And since I knew that already, I make all the labs worth, guess what, 25 points. So what I do at the end of the course, I will average your labs together, drop your lowest score. And by the way, on this Blackboard that we have now, on the old version of Blackboard, if I wanted to drop a score, I said exempt the score. In other words, it took it out and didn't put it in the calculation. This new Blackboard, this Ultra, does not have that capability that I've been able to find. So what I have to do is just remove that score from the grade book. And last term, is sure enough, when I did it, I had students emailing, hey, I don't see my lab 1 and 3 in there anymore. I did it. I remember turning it in. You had it on there. It's not showing up anymore. Or, hey, what happened to my test 4? You know I did it. You know, you had a score before. Those are the ones I dropped. The only way I can drop them in Blackboard is to take them out. So if you see that happen at the end, don't panic. Those are the ones you get to drop. Okay? So, now if you don't turn one in, it'll show up as a 0, unless that's the one you drop. Okay? So, that's the difference. If you see it not listed, that means I used it as a drop. If you see a 0 there, that means you didn't turn it in and it got counted as a 0. Okay. So I'll average your labs together. That's 25% of the grade. It's going to be a number between 1 and 25. Okay. So that'll be your lab. Now, what I do with the others, the average of the paper, the remaining test scores after I drop 1, if that helps you score, and the comprehensive final exam, the average of those, I will take 75% of that, add it to the 25 from your, or whatever portion of 25 from your lab score. That will be your final grade. Okay? It'll be something between, hopefully, between 60 and 100. Hopefully between 70 and 100. Don't go any lower than that. The comprehensive final exam cannot be dropped. So don't come to me at the end of the term and say, hey, I've made all A's on all my tests. Can I drop the final? No, you can't. That's required. That's one of the core competencies of the class, is that comprehensive final exam. I will drop one test score, chapter test score, but not the final. And you know how we grade. 90s are A's, 80s are B's, 70s are C's. Don't go any lower than that, okay? I'm not going into this. The dean or somebody, whoever wrote this, had this all screwed up down here about rounding. This is correct, okay? Now, the dean has also come up with this for the virtual classes that we didn't have before. She wants us to have some type of input from you after every class, okay? I'll tell you right now, I'll tell you in a few minutes what today's requirement will be, okay? That will be your participation grade, you might call it. It doesn't really count as a grade. What it does, I'll mark it in the grade book, not on Blackboard. There's no way to do it there, but in my physical grade book that I have here, I don't have you in there yet, but you will be in there. I'll put checks there that you've turned in the daily work. And if you've done a good job of turning that in, if at the end of the term you wound up with something like this, a 79.4, I would bump that up to a B. It wouldn't stay a C. But if you didn't turn in the daily work, that would remain a C. So that's where the daily work will help you. If you happen to come out right on the borderline, and it doesn't have to be that close to the borderline, but right on the borderline, that will bump you up a letter grade, okay? It's not going to bump an 83 up to a 90. It won't do that, but it will maybe bump an 89 to a 90, okay? So, anyway, that's what your daily score is. We'll talk about that a little bit later. Here is what we always said in the syllabi about attendance, but the dean has had us put in 3 more paragraphs about virtual classes. And those next 3 paragraphs here are those paragraphs. So try to be here every day. Nothing replaces reading the book, but also nothing replaces being in class. You get to ask me questions, something you don't understand. If you just rely on the YouTube videos, you can't ask a YouTube video or question. It just sits there, okay? It can't answer. So please try to be here every day. Like I said, I may be a little late getting here, but I'll be here because I have 5 minutes in between my 2 classes and I've got to set up everything, take down one. Like today, I had forgotten to turn off the Screencast-O-Matic and I had forgotten to take down the PowerPoint. So I'm going to try to get better at that, but this having only 5 minutes between classes is outrageous, okay? But that's how she set up the schedule, okay? Now, withdrawals. Since all of you are Lawson students, let me say a little bit about this. If any of you are on financial aid of any nature whatsoever, Pell Grant, VA, scholarship, whatever, okay, generally a D or an F is not going to help you at all, okay? In fact, it will lower your grade point average. I hope a D will lower your grade point average. The only way it wouldn't is if your grade point average is less than 1.0, okay? That's the only way a D is going to help your grade point average if your grade point average is a 0.7 or something like that. So hopefully none of you are in that boat. So a D or an F is going to hurt your grade point average and it's not going to help your financial aid situation at all. We'll talk about this a little bit later too. So hang on to that thought. A withdrawal doesn't help your financial aid any, but it doesn't hurt your grade point average a bit. A W does not hurt your grade point average at all. So if you get way behind in the course and there's no chance you can pull out a C or better in the course, my advice to you is to withdraw. Now, if you've withdrawn from the same course before, or made a D in it before, or made an F in it before, and you withdraw this time, Pell Grant will not pay for it the 3rd time. They'll pay for 1 retake, but not 2. But guess what? If you're going to make a D or an F, you're still going to have to take the course again. They're not going to pay for it. That hurts your grade point average. A W does not. So consider that. I'll let you decide, but a W is far better than a D or an F. Now, a C, I think, is better than a W. Some students disagree with that, but that's your choice. But a W is better than a D or an F, always. Makeup work. Now, since y'all have decided to have take-home tests, and since you've decided to do, and you do your labs and get those in, I don't know what makeup work is, okay? I'll record everything that I can from the class so you can make up anything you may have missed by watching the YouTube videos. Okay, now let me say this. When I give you the labs or the test, try to get them back within a week. Now, why do I say a week? There's two reasons. One, you always have one class day in between to ask questions, to say, hey, I don't understand what you mean by this. How do you do this? Now, I'm not going to say, here's a question I will not answer the way you want me to. What's the answer to number 7? I'll not tell you, okay? But if you tell me what your problem with number 7 is, I'll try to help you figure out what it's talking about, okay? So I won't answer the question of what it is, but I'll always try to help you find a way to get that answer, okay? So always try to get your test and your labs into me within a week. Now, if you need more time, that's okay, but don't put off one test until it's after time to take another test. Try to get them done before the next test gets out there, okay? And with a 10-week, or we don't even have a 10-week term, and 9 tests, that's going to be at least a test a week. So we're going to be hopping, folks, okay? Now, lateness policy, like I said, I'm going to be probably a little late getting started every time. Try to be here on time, but get here whenever you can. Now, let's talk about these next. Academic integrity, here's my suggestion. Have it. Practice it. Use it. Okay? Conduct yourself with honesty and integrity at all times. That's just a given. Plagiarism, don't do it. Okay? Just don't do it. It's not going to help you any. Write your own paper. Do your own work. In labs, you can work together, but do the work. Get the idea, the concept of the chapters. That's what we're after. Cheating, don't do it. There's just, if you need the course for any reason at all, get the benefit of the course. You're paying for it, get the benefit of it. Learn something from it. Okay? Now, this next one is one of my favorites. Professional decorum. Okay? Especially in a virtual environment, folks. I don't want you sleeping during my class. If I catch you sleeping during the class, I'm going to be really up. How will I know if you're sleeping? Unless you have your microphone on and you start snoring, I'm not going to know. You could be reclining or lounging. I will never know. So please, this is almost for in class, okay? Unnecessary traffic in and out of the classroom. Look, you can go anywhere in your house you want to, can't you? I will never know, okay? Eating or drinking, I actually have a glass of water here and also a can of Coke. If I get really tired, I'm going to take a little caffeine, you know, or if I get dry from talking too much, I'm going to grab a drink of water. You know, you're at home. Do whatever you want to. Or wearing inappropriate clothing, my word, if I see you in any inappropriate clothing, I'm going to write you up. Nah, this is nuts. Sunglasses, I don't care if you wear sunglasses. You're at home. You can do whatever you want to. Hats, I don't care if you wear a hat. You're in the home. You can do whatever you want to. If you got on earphones, hopefully you're listening to the lecture, but I can't help it if you're not, okay? So that's sort of ridiculous. I probably spent too much time on it. Course concerns. Now, this is where you are having problems with me or with the course. You're not able to understand something or get something. Please get in touch with me. Let me know what the issue is. We'll try to work it out, okay? For instance, in the last class, when we did go to virtual class in it, I found out that some of the virtual labs that I had planned to use, some of the students could not open them. Their computers did not have the right version of Java or something like that on it. And even if they tried to load it, it still didn't work. They could not get certain ones of those labs to work. So I had to quit using those labs. So let me know if something's not working. Okay, we'll try to work around it. If you are unsuccessful going through me, go to the department chair. Oh, that's me. No, okay. It's actually for this class, it's actually Dr. Wilson. She will get on my case. If not there, Dr. Pruitt. He's hers and my boss, okay? If not there, Dr. Davis. She's all of our bosses. And if not there, Dr. Crawford. He is the vice president. He's in charge of everybody. And if not there, go all the way to the president. I'll help you get there and write me up or whatever. No, let's just handle it as the lowest level possible. But if you don't feel like you're getting satisfaction, please move along. I'll help you get up there. Okay, discrimination, harassment, we don't like it. We don't want it to happen. Don't do it. I really don't know how you would in a virtual environment anyway, but if you sense that something's happening, let me know. We will do our best to stop it, period. Okay? Now, I don't know about this class, but in some of my other classes, I've already received from Dr. Herndon or Miss McCoy-Jones information about students with disabilities. If you have any kind of disability that's going to affect your being able to perform this course well, let Dr. Renee Herndon, I can't find the cursor, there it is, Dr. Renee Herndon, or Mrs. Janine McCoy-Jones. These are the phone numbers on campus. They may be on campus some. Some of the people are going to be on campus some, but email them, okay? And you can go to lawsonstate.edu, to our website, and there you can look for the Student Services blue tab, Disability Services, ADA link, meet or contact the ADA counselor link. There's various ways you can get in touch with these people. Let them know what your issue is. They will let me know what I need to do. But look, hey, take home tests. You're doing the labs at home. You're writing the papers at home. I don't know what else we could do, but if we can do something, we'll do it. If you want me to talk louder, I'll talk louder, okay? If you want me to slow down, I'll slow down. You know, whatever it takes, we will try to do. Now, this is the college calendar, which came right out of the academic calendar that's on the website. I didn't put everything here, but let me point out a few things, okay? Number one, and this really irritates me like crazy. If you'll notice, this is our first class. And we are a week into school. The Tuesday and Thursday classes have already met twice. You had not met at all before today. When I went to the calendar committee, I wasn't able to go for the most recent time, but when I've gone, I begged them repeatedly, please do not ever start a class on a term on a Tuesday or a Thursday. Always start the term on a Monday or a Wednesday. The reason is every term, fall term, Labor Day, spring term, Martin Luther King Day, summer term, Memorial Day. We just had it this week, okay? All three of those, within the first few weeks of class, couple weeks of class, we have a Monday holiday. So if you start a class on a Tuesday or a Thursday, start a term on a Tuesday or a Thursday, they get an extra class before Monday, Wednesday, and then Monday, Wednesday loses a class. So in no time, like this term, we're already a week behind Monday, Wednesday. Okay? Now, not only that, but coming up on the 4th of July, Independence Day is on a Saturday. They had a choice to go the holiday on Thursday, the 2nd, or Monday the 6th. Guess what they chose? Monday the 6th. I emailed them and said, please, if there's any way, can you change this to Thursday the 2nd, so the Monday, Wednesday classes don't get a week and a half behind? Not an answer back. They just completely ignored my initial request and again. So we are going to be pushing it to get everything covered. Okay, that's one thing I wanted to say about the calendar. Okay, another thing. Actually, drop ad ended last week before we ever met. Okay? No, yesterday before we ever met. If something has to happen, I think it can still happen. Okay? Now, some students get these confused. Friday, June 12th is the last day to withdraw from college. Withdraw from all your classes and still get a partial refund. Okay, that's if your family moves, you get sick, somebody gets sick and you have to become a caregiver, there's some reason you just can't go to school this summer, that's what this is talking about. If you withdraw from classes, all your classes, by Friday the 12th of June, then you get a partial refund and you're out. Okay? Now, down here is something different. This is the 60% completion date for Title IV funds. That's Pell Grant and things like Pell Grant. If you withdraw from a class, not from the whole term, but from class before this date, Tuesday, June 30th, then you may owe them money because you haven't finished 60% of the class. If you withdraw after that date, then you don't owe them a thing. Okay? So that's an important date. If you figure out, hey, I can't handle this, it's too late to drop ad, you're not going to withdraw completely, wait until after the 60% completion date, which is June 30th, and then withdraw. Okay? Now, as I've already said, griped about Independence Day. Unfortunately, they made that holiday a Monday rather than a Thursday. I tried to get them not to, but they wouldn't listen. Now, the last day to withdraw from a class, that's Tuesday, July 21st. Okay? If you don't withdraw by that date, you're not withdrawn. You have to, I would say, suggest that you try to withdraw between June 30th and July 21st. Don't do it before June 30th or after June 21st. Okay? Final exam will be Wednesday the 29th. Actually, I'll give it to you the last day that we meet, which would be Monday the 27th, and you get it back to me by the 29th. Okay? If you need an extra day or two, 30th will be okay. 31st will be okay. That's a Friday. Or the following Monday would be okay. Don't give it back to me on Tuesday the 4th. You're probably not going to get a grade. You'll get it incomplete until I get it graded, because grades are usually due in by noon on that day. I don't have time to be grading a bunch of finals coming in late or research papers coming in late. You'll get it incomplete until I get them graded. Okay? Is that understood? Try to get it to me by Wednesday the 29th. But that's a long way off. I'll be harping at you a lot before then. Okay. Here's today's assignment. I said they wanted one every day. Here's what today will be. If you go back, read through the syllabus, and if you understand everything, if there's something you have questions about or not sure about, then ask me. Either an email, message me on Blackboard, or wait till next class. But ask me. Then either type your name or print this out, sign your name, and then email and put the date. Send it back to me. That will give you credit for today's assignment. Okay, everybody understood that? Any questions?
Yes.
Okay, good deal.
Yes, sir.
So that's today's assignment. Other days it'll have something to do with the course, but this will be this for today. Any questions on the syllabus? Ran it into the ground, didn't I? Okay. So let's end the syllabus, and you'll probably lose screen sharing for a moment, but I'll get the next thing up. And Harry says, take home. Okay. Harry was encouraging everyone to vote for take home. Okay. Good job, Harry. Okay. Let me minimize this so I can get to...
If I can, Professor Fowler, this is Harry C. Wright again.
Right.
Did you say the homework is that form, that acknowledgement form?
Yes.
Okay, cool. I'm sorry, I just got on a plane. It's kind of hard to hear.
Oh, really? Where are you flying to?
Maryland.
Wow. Be safe.
Will be.
All right. Good deal.
Thank you.
All righty. All right.
Awesome.
Here we're continuing. We've done the syllabus. Here's my locator card. I told you I would show it to you. Here it is. You click on it there, but here you have to hit the 3 dots. It downloads, and once it finishes downloading down here in the lower left corner, click on it, and here it comes. Slowly but coming. One of these. There it is. Okay, you can't see it yet. Let me minimize this so I can get back so you can see it. I don't care about that. I don't know what this is doing. Okay, I'm trying to minimize it. Okay, there we go. Let me get back to Zoom here. Okay, can you see me now? Okay, I'm going to share the screen. And it was, is it there? Okay. It was there, but I guess I minimized it. Hold on.
We see the screen. Well, I see the screen now. I'm not sure about everybody else.
Okay. Can you see my locator card? No, it hasn't. Let me get it back.
No, it hasn't pulled up yet.
Okay. It's coming. There it is. Took a while, but it got here. Can you see it now?
Yes.
Locator card. Okay, summer 2020. My name's still the same. I have no office phone. My email account's still the same. I will be answering emails as I can. I'm in charge of mathematics. This course, I probably should change this and make it for natural sciences, but you understand. It's the same for whatever. Okay, my department is mathematics. So let me get down so you can see my whole week at one fell sweep here. There, we can see it all. All right. On Mondays and Wednesdays, I did have a class then, but they gave it to somebody else. So that's from 8 o'clock in the morning until 10:30. I'm here in the office, okay? And we'll talk about the difference between office and office advising in just a minute. I usually eat lunch sometime after 10:30, so I'm not necessarily in the office then, but I'm usually back before 11:30 because at 11:30 it starts my Calculus 2 class. I'm in that class until until 2:25. That's right before this class, and that's the one I've got a big 5 minutes before it starts. And then this class starts at 2:30. It goes until 4:45. Then we have the lab. It goes until 6:15. Now, a lot of days our lab will not take us a full hour and a half. In fact, some days we may not even have a full lab because maybe we'll do the lab the next day. If we don't, we may continue class on this day and then start lab earlier on Wednesday or vice versa. Let me move this out of the way. It's bugging the fool out of me. You can't see it, but it's okay. All right. So, but anyway, if I do set you up on the lab, you get going, you ask questions, you're ready to roll on it, I'll say, do you want me to hang with you on this in case you have more questions, or do you want to do it on your own? And most of the times the students will say, we want to do it on our own, get out of here. So I'll go on and end the Zoom at that point. But if anyone wants me to stay with you, I'll stay with you as long as possible, up until or even after 6:15. Okay, so that's my Mondays and Wednesdays, pretty much. On Tuesday, I'm in the office by 8 every morning. My first class on Tuesday and Thursday is at 8:30. It's a differential equations class. It goes until 10:45. And then I'm in the office swapping up materials for classes for 15 minutes. And then my linear algebra class starts at 11. That goes until 1:15. Now, sometime on Tuesday and Thursday after 1:15, I'll run down and grab a bite to eat. I'm usually back here before 2:15. Now, again, you'll see office is 2:15 until 3 o'clock. Now, here's where you see office advising. What's the difference in office hours and office advising hours? Well, did any of you use the virtual advising center to register for the classes?
Sir.
You did, okay? So you know what that is. You go to the virtual advising center, you pick a time and or a instructor or a faculty member or a administrator, whoever you want as an advisor. You pick a time when they're advising and then you sign up. Well, that's what office advising is. I'm down for 5 hours a week, So my 5 hours are on Tuesday from 3 to 5, so it's right before this class starts. Most of the time I don't have an advisee in there from, I don't know why this does this. Okay, forget that. Okay, unless I have someone that signed up for 4:30 to 5, most of the time it doesn't take 30 minutes, but if they did sign up 4:30 to 5, first thing I'm going to tell them at 4:30, I've got to be out of here by 5 o'clock, okay? So we will end it a little early so I can start my class on time. But if there's sometimes that I'm running a little late, I'm sorry, that's not this class. That's Physics 112. Forget that. You're over here, okay? I'll tell that class. I've already told him that. Okay. So my physics class starts at 5 o'clock and it goes until 6:30. So most of the time during this office advising, I'm in the office not advising. For instance, yesterday, I don't think I had a single student all afternoon. This morning, I didn't have a single student. I may have had one yesterday afternoon. And I think tomorrow afternoon, I think I've got one. Okay, so there's not that much. As we get closer to fall term, I'm sure more of these time slots will fill up. But you won't know that. I won't know that until the day before. So that's the difference between office and office advising. Office, I'm guaranteed to be here. I may be on the phone with somebody or I may be doing something else, but I'll be here. Email me, try to contact me. I'll be here. Office advising, if I don't respond immediately, it may be because I'm advising a student. Okay, so Wednesday is just like Monday, except I have office advising from 8 to 10. And then I'm just regular office hours from 10 to 10:30. Yes, question? Okay. Thursday is just like Tuesday, office in the morning, office again between classes, office then right after lunch, office advising starting at 3, but only going till 4 because I only do 5 hours. 2 hours on Tuesday afternoon, 2 hours Wednesday morning, 1 hour Thursday afternoon. So I have office hours, free office hours from 4 to 5. And then I'm in class from 5 to 6:30. Okay. The college is not operating on Fridays. That doesn't mean I won't be checking emails, but I won't be doing it as on a regular basis like I normally would during the week, because my wife will have plenty of things for me to do on Friday, and in between I'll be checking emails and trying to stay abreast. Okay. I'll also check on Saturday, Sunday too. She fusses that I spend too much time. Any questions on my locator card? Okay, I'll go on and end this one so you'll lose screen sharing for a moment. Okay, and let me go and pick up the next thing on Blackboard. Okay, you probably can't see that yet. Let me go close this. And now research paper instructions. Remember, I promised we would do these. So let me click on that, get them to open. Okay. Once they get open, I'll pull you back in to screen sharing. Okay. Well, that's not how I wanted to do it. Wait a minute. I figured out the better way last time. Okay. Better to get my Zoom going here. Okay. There we go. Okay, can you see the research paper instructions? Anybody?
Yes, sir.
Okay, good deal. So here's the research paper general instructions. You choose a topic, any topic you want to, that deals anything with astronomy, earth science, weather, climate, or anything to do with the Earth's waters. Okay? Lots of topics to choose from. You can choose a person. In the text, you'll see that there's at least one person highlighted in every chapter. But usually when they highlight that one person, they'll talk about 3 or 4 other people. If you wanted to write on a person, you can write on a person. You can write on the theory. We'll have one, for instance, the theory of plate tectonics, the theory of global warming, theory of continental drift. Okay, there's lots of theories that we will be hitting around and dealing with. You can choose one of those. A phenomenon. Okay, something like the black hole. Okay, I didn't even mention before the Big Bang Theory, not the television show, but the rest of it. Okay, phenomenon like a black hole, a quasar, there's just tons of things you can pick up on that. An application. Okay, I really like application papers. If any of this applies anything to your field of study or your interest, say if you're a stargazer, you love going out and look at the stars at night, and you want to write on something to do with that, fantastic. Okay, if you're a gardener and want to write on how to conserve soil or water or something like that, that would be, I mean, anything such as that. Any other such topic about which you have an interest and can be related to physical science. Or it could be on an internet application or demonstration which you find useful to the class. For instance, I've been talking about plate tectonics, and you don't have a clue of what I'm saying. And in the book, it doesn't help very much, but you find a website or a YouTube video or something else that describes it and shows it, and you say, oh, that's what they meant. If you want to write on how that opened your eyes and made it real to you, you can write a paper on that too. Okay? So what I'd like you to do, maybe on that first assignment, when you send me that page from your the syllabus, why don't you go on and type or write on that page what your research topic is. Now, you can change your mind later, that's fine, but at least give it some idea and think on that and send that. If you want to go on and send me the page from the syllabus and then later send me your research topic just in an email, that's fine too. Okay, but be thinking about it. I want you to get that to me within the next week. A day or two would be fine within this next week. Okay, now you'll need to find at least one, but two or more are better, outside sources for your paper. Now, what do I mean by that? This textbook is a great source of ideas for your paper. Like I say, they feature a person in every chapter. They mention theories or phenomena or things in every chapter. However, the text can be a great source for ideas, but it's not a source for the paper. You have to find your sources outside the book. Okay? The book can give you the ideas. You go find your source outside. Okay, Parisha must have had to leave. Here she's coming back. Okay. All right. Now, I see Parisha's back. Good deal.
He said, I see Parisha's back. Good deal.
I'm sorry? Okay. Okay, I think she turned her mic off. Okay. Now, your paper must be at least one word process page of text, double space. Now, these instructions are single space. I want you to double space. Okay? That would be like this much space between every line. Okay? Not just between the paragraphs. Okay? I want standard font. This is 12 pitch, I believe, or 12-point font. That's what I want you to use. That little bitty stuff like 9, that's hard to read. The great big stuff, that's going to fill up the page too fast. Don't want that. 12 pitch or 12-point font. Use any font you want to, as long as it's nicely, easily readable. Okay, I named just a few. There's tons of them out there that are very good, clear fonts. Don't get any fancy curlicue that make it difficult to read. Try to keep the paper less than 2 pages. Oh, let me talk about what I mean by a page of text. Now, you don't have to, but a lot of students will put a header up there and then skip a few lines and do their title and maybe skip another line or 2 or 3 and then start typing right here. Well, what's a page of text? A page of text will go to the bottom. I didn't mean to do that. Okay. We'll go to the bottom of this page, all the way to the bottom, and then on the second piece of paper, start at the top and come down at least that far. That's a page of text. Okay? Keep your margins reasonable. Don't make them so big. Don't make it big at the top, bottom, or sides. Keep them very reasonable, but you'll need to turn in at least 2 pieces of paper, okay? Because you'll start typing one place, and on the second piece of paper, type at least that far down on the second page, okay? So, but then try to keep it less than 2 pages if you can. Now, you'll lose points if it's too short. There is no penalty for being too long. There's no such thing as a paper that's too long, except for this. Do not try to replace quality with quantity. Now, I've been teaching here 20-some years, and I haven't missed a term, and every term I have between 5 and 8 courses a term, so I've seen up. And most of my courses have papers, except first year or two maybe. So I've seen an awful lot of papers. This has only happened a time or two, but I just want to warn you about it. Don't try to replace quality with quantity. And I've had a few people that turned in papers that just went on and on and on. Now, I've had some long papers that were excellent papers, but I've had others that were not good papers, and it seemed like they just said, if I make it long enough, he'll be impressed. No, I won't. Here's how I grade your papers. When you turn it in to me, it's a 100-point paper, okay? As I start reading it, then you start losing points if I find errors. I know you'll say, don't read it, don't read it. No, I'm going to read it, guarantee you. You put the work into it. To do it, I'm going to read it, okay? So, if you turn in a really sloppy paper, but make it very, very long, guess what? That's more and more and more and more points you're losing. So don't do that. Turn me in a good paper, whether it's 2 pages or 3 pages or 4 pages. If it's a good paper, you're not going to be losing many points, okay? Turn me in a good paper. Try to keep it between 1 and 2 pages, but if you got so interested in the subject and you need to go another page or two, go another page or two. I guarantee you, if you're that interested in it, I'm going to enjoy reading it. But I don't want to read something you just put out there to just throw more of it against the wall. That's not what I want, okay? So try to shoot between 1 and 2 pages. Be sure you have at least 1 and end it as soon after 2 pages as you can easily do so. Okay. You can use any standard format you want. Most English classes teach MLA, that's Modern Language Association format. Fine with me. I have no problem with it. A lot of science areas use APA, which is American Psychological Association. They came out very early with an excellent format that's good for journals and stuff. If you want to use that, you certainly can. I belong to several professional organizations. It seems like every one has a different format they like to use. Any format you choose, be consistent. That's the main deal. Be consistent. If you start blocking paragraphs, block all your paragraphs. If you start indenting your paragraphs to here, indent all the paragraphs to there. If you start in Arial font, don't change the Times New Roman in the middle of the second paragraph or anywhere. If you italicize for emphasis, that's fine. But make sure it's for emphasizing, not changing and writing your whole paper in italics, okay? Be consistent, okay? Also, be consistent in how you reference your sources. I've had this happen a few times, not many, but I have had it, that someone references a source up here in this paragraph, they open a parentheses, and they say, type the author's last name, comma, year of publication, close it. If that's what your format calls for, fine, okay? But then down here, they'll have a very similar source, but a different source, but the same type of source. They open parentheses, and then they put the title of the article, comma, page number, close parentheses. Hey, they were the same type of things. Why did you use different formats for giving your sources? Well, I think I know. This source probably used the format you copied from it. This source may have been using a different format, so you copied its format. No, you choose your format and do all your citations by that format. And then when you list the work cited or bibliography or whatever you want to call it, then I'll know which one you're talking about. Okay, so be consistent. That's the key. Also, spelling, grammar, sentence structure, all those types of errors will cost you points. So use spell check, use grammar check, use good proofreading skills. But your content also matters. So if you have inconsistencies in your text, okay, Parisha must have had to go and come back again. Okay, so
I have a question.
Okay, yeah.
So it doesn't matter to you if we prefer footnote or if we prefer putting footnotes at the end, at the bottom of the paper, or doing a bibliography at the end of the entire paper. It doesn't matter to you.
Doesn't matter to me. You follow the format you've chosen and be consistent with it. That's perfectly fine. Now, I've also had this, and this has been more than just a few times, that people have apparently copied something from somewhere and put it in there, and in doing so put in a reference to a footnote, but never put the footnote. Okay, so there again would be an inconsistency. I know you wouldn't do that, but I have had it happen by some lesser classes than yours are. Okay, so anyway, be consistent. Now, when is the paper due? The last day of class before final exams. Okay, not the last day of finals. No, the last day that we meet as a class. When I give you the final exam, and it's due the next Wednesday. Okay, so that Monday, the last Monday we meet as a class, that's when the paper's due. But please don't put off your paper till that last day of class. Okay, and here's 2 reasons for that. One is my past experience. My past experience, now this is a generalization, okay, but in general, the papers I get in early in the term are usually some of the best papers that I have. Now, always, I've had some real dogs at the beginning of the term, but then as the term goes on, it seems like the quality, in general, tends to go down, okay? Now, I think I know why, because you put off doing the paper and suddenly you say, oh, I got the paper due, and you just throw something together, and it's not good quality work, okay? Usually early in the term, you have more time to do a good paper than you will later in the term. So please do it early. Get it to me early. The second reason is selfish. I don't want to be grading papers that last week and then final exams and everything else all at the same time. I want them spread out throughout the whole term. So here is the stick, okay? If you turn in the paper after that last day of class, that Monday that we meet, if I receive it after that, you are losing points. There's the stick. Here's the carrot. If you turn in the paper this month, the month of May, now you only have a few days left in May, if you get it to me during the month of May, you get 2 bonus points. Whatever your score is, I add 2 more points to it, okay? Now, if you turn it into me the month of June, you get 1 bonus point. If you turn it into me the month of July, you get your score and just your score. So please, get me the paper as early as you can. Get me your paper topic soon, very soon, and then get me the paper as soon as you can after that, okay? Any questions? Now, I require one more thing that most English teachers I don't think require, and anybody else. It's just something, a pet thing of mine. When you submit your paper, please attach a single page from one of your sources. So let's say you had 3 sources. Pick a source, any one of them. I don't care which one, okay? Let's say that may be a journal article that you found in the library or a book you found in the library. Well, take it, if you were in the library, or if you have the book at home or something like that, take it, get a copy of it, and send me a copy of that page. A single page. I don't want the whole article. I don't want the whole chapter. Just a single page from one source. Not all your sources, just one source. What if that was a source you found on the internet? Okay, just print me a single page from one source. Now, what if your paper was that YouTube video that you found that really explained something for you? Well, it's hard to get a page out of that because that was a video. So just send me the link from that video. okay? And that will be suffice as your source, okay? If I like that link and it's something that I think would be useful, I'll be adding that to the Physical Science 111 classes in the future as a link that they can go to and get good information. So give me a single page from one of your sources or a link if it's your computer application. Any questions on the research paper? Okay, there's my name, there's my email. Get me your paper topic as soon as you can, and as soon after that as you can finish your paper, get me your paper.
Can we send it in the messages on Blackboard?
Okay, you can send it either as an attachment to a message on Blackboard or an attachment to a regular email. Whichever is most convenient for you to do, either one is fine with me.
All right, thank you.
Good deal. And some people, I actually had one person in one of my classes last term that preferred mailing me some of her work. I don't know why. Maybe she didn't have a good way to scan, or her phone wouldn't take good pictures. I don't know why, but she mailed me her stuff. Now, you have to get it to me early, so I'll get it in time to grade it, but that would be another reason to get it done early. But I'll accept the letter in the mail too, okay? I've only had one or two students that have chosen that route. All right, any other questions? Great question. Okay, what I'm going to do now is get out of the research paper, so I'll lose you on the screen sharing. Okay, that paused. And let me go and get the next thing in Blackboard. Okay, that was a research paper. The next thing is the YouTube videos. Now, I think I'm going to pull you back in to see this, because I think it'll continue in the link. Okay, can you see my Blackboard page?
Yes.
Okay, good deal. I'm going to get this thing as much as I can out of the way. You can't see it, but it's in my way. Okay. Here is a link for the YouTube videos. I'm going to click on it now. It goes straight to the videos. Links do that. Documents don't, but links do. Now, guess what? We're not going to have a field trip this time, so I'll probably leave that in there, but I may go on and take that out. Okay. These are from previous terms. In fact, last spring, this was the syllabus. These were YouTube videos from terms before that. For some reason, I left them in here. I'll leave them in there now, or I'll take them out, whatever. After today's class, I'll take out this syllabus thing, and I'll put the new. The older things are always at the top. The newest things, the things I'll be adding, they're going to be at the bottom. So today's things will be at the bottom, and it will be PHS111 Syllabus, just like it did at the top there. So here's why I leave these in here. Sometimes, believe it or not, technology fails, okay? And if we miss a class because the supercomputer goes down, my internet service goes out, or something like that, and I can't record the class, you'll have that class recorded from the previous term. So I'll leave them here. So, but as we do new stuff, then I'll add it at the bottom and take it out at the top. Does that make sense? So always the old stuff's at the top, the new stuff's at the bottom. And that's how you get to see it. All you do is go and click on this, and you get to see and hear the entire video. Okay. Now I'm going to try to continue and record our labs. So if you missed a day of class of lab, go to the video and you'll see what we're doing to do the lab. Okay? Any questions on the YouTube videos? Okay, it's a link. It goes straight there. So I'm going to end that. Okay, now, this next thing is something that a student sent me many terms ago. These are pictures from the Hubble Space Telescope. We'll be talking about who in the world Edwin Hubble was. He could be a research paper topic. We'll be talking about the Hubble Space Telescope. That could be a research topic. It's a very interesting story with that. But there's 10 pictures here. I'll open those. Anything that's a folder like this, you can click and open them. I just opened the 10. I'll just show you 1 or 2 of them. All you do is click on it, and hopefully it comes up. All it is a picture taken by this Hubble Space Telescope. Okay? Incredible pictures. Okay? You can fiddle around with it, look at it more closely. That's a galaxy, I think. Okay? Something like the Andromeda, but not the same. In fact, it looks like it's a collision of 2 galaxies. I don't know if there's some paperwork here that goes with it. I guess not. I had some verbiage that went with it, but they're just incredible pictures. They were so pretty, I decided to put them out there for you to look at, for your viewing pleasure. Incredible pictures from the Hubble Space Telescope. They're sort of old. Let me, Valerie's in the way here. I've got to go. Okay, there she is. Okay. So I'll close that thing. So anything that has this symbol, that's a document that you'll have to open, upload and open. This is a folder. Hit the arrow over here and it opens up the folder. These are links. You just click on the link and you go to the link. Okay. So let's look at space objects in perspective. I'm not going to go over this in gory detail, but click on that and see what's here. Again, this is something a student sent me. So I'm going to open it up, and it's pretty interesting. Oops, I'm sorry. Only need 1 click. Download the original file, and once it comes up, click on it, and it's a really interesting little, basically it's a PowerPoint show, I think. Okay? Well, not really a PowerPoint show. It just shows these are called the 4 terrestrial planets. We'll talk about this in chapter 15. Pluto is not considered a planet anymore, but when this was put out, it was. It just shows you relative sizes. Earth, slightly larger than Venus. Both of them are much larger than Mars and much, much larger than Mercury and much, much, much larger than Pluto. That's one reason it's no longer considered a planet. It's very, very small. By the way, our moon is close to the same size as Mercury. Not quite the same size as Mercury, but close. So this just gives you an idea, and it just goes on and on and on. Incredible representation of relative sizes. I'll let you watch this on your own viewing pleasure. Let's see, maybe page down will work better. Yeah, and there's Jupiter, Saturn, Uranus, and Neptune. There's the Earth compared to the 4 gas giants, okay? And there are Venus, Mars, Mercury, and little old Pluto there, which is no longer a planet. Oh, y'all can't see this, can you? Sorry, why didn't you tell me something? Why didn't you tell me something? Okay, can you see that? Can you see it?
I can.
Okay, this is what I was talking about. That's space objects in perspective. I'm not going to go through the whole thing, but just giving you a flavor of what that's all about, okay? And there's the sun and all the planets compared to the sun. Really interesting how they've done that, okay? So I'm going to get out of this and go back to, and that's something that some students sent me, okay? And I thought it was so good, I included it here, okay? So let me go back to this. Back to Zoom. Back to screen share. Oops. Where is it now? There it is. Okay, there's my syllabus again. Y'all can see it? That was space objects in perspective. Just a fun slideshow, you might say. It wasn't quite a slideshow, but something like that. All right, here are the PowerPoints. Again, they're in a folder. Come over here to the arrow, click on the arrow, and the folder opens up. Okay? And we'll be starting with chapter 14, PowerPoint, then 15, 16, 17, 18, 19, 20, skip to 23 and 24. Those are all the slides we'll use all term long. Okay? The reason I put them there, if you want to look at them ahead of time, you certainly can. If you want to print them out and write on them and take notes on them, you can do that. However you want to use them, it's up to you. Okay? And I think that's the last of my content in Blackboard. Okay, any questions on Blackboard? Anything about the course? Anything? No? All right, let's see if we can get started. Let's see, this class goes until 4:45, and then supposedly we start the lab. Well, today, basically all this stuff has been more like a lab because we've been doing it together. So we'll start the class now and go until 6:15, okay? Let's see, if we start now 4:15 to 6:15, that's going to be less than what our usual class would have been. So let's get out of this. I'm going to end my content here. And actually, I'll get out of Blackboard altogether, I think. Oh, screen sharing is stopped. Let me go to here. This should be our PowerPoint slides. No, that's not. Okay. Let me try again. New share. Well, yuck. I know they're out there somewhere. Oh, here they are, right here. Okay, let me minimize this again. Yuck. It's not the one I wanted to minimize. Okay. All right. This is the one I want to have in front. Okay. I take it, can you see the PowerPoint? You probably can't, can you? No. There we have it. Boy, that took a long time to get there. All right. Can you see the PowerPoint now?
Yes, sir.
Okay. So, I take it that most of you don't have a book yet. So I'll be making reference to the book and mention a few things. I'll not go into as gory, well, let's see how to say this. I will probably add more detail now just because you don't have your books to look at. Once most of you have a book, an ebook or used book or something to look at, then I won't have to do as much detail. But this is chapter 14. We're starting big, the universe, everything that there is, and then we'll go smaller from that. Now, this is a very pretty picture, probably taken from the Hubble Space Telescope. What this is a picture of is probably what was a supernova. Okay? What happened? This star ran out of fuel. It couldn't produce any more fuel, and we'll be talking about what I mean by this later in this chapter. And it basically collapsed on itself and then exploded outward. So what you see out here are the gases. I'm going to move this. This is in my way again. Okay. These are gases out here exploding away from the center of the star. What was the center of the star is that little point in the middle there. And what that has become is called a white dwarf. Don't worry about this yet. When we get to it, you'll know what I mean by a white dwarf. But this is a picture of a star that's in the process of exploding. Now, when I say in the process, this could be taking hundreds of years to happen. This may be several hundred years after its explosion. The stuff is moving away. What we're dealing with is spatial areas so huge you can't even imagine it. And this is a picture of that. This is called a planetary nebula. What a nebula is a mass of gases, and that's what the star started as, and that's what it's ending as, a mass of gases circling the center, and that center is a white dwarf. Now, you don't have to know what these terminologies are. They're somewhere way out there. If you're looking and you wonder, what are these things? That's probably some galaxy far, far away. There's probably another one, maybe two, real close to each other, another one. The rest of these are probably stars, some bright stars and some dim stars. But that's a white dwarf in the middle, okay? It could be these are very bright stars, but usually they don't show up that big on the Hubble Space Telescope, unless it's slightly out of focus, which it may have been, okay? But that's just a flavor of what we're going to be talking about in this course. Well, in my last class, the PowerPoint would only advance with the arrow key. Now I can't get it to advance at all. Okay. I think I have to hit. Okay. If I do anything with Zoom, then my cursor doesn't work until I do something else. Here's the core concept for the chapter. And if you have a book, it's on page 353. If you have a small book, it's probably right near the beginning. So it may have a number 14-1, okay? That means it's 14th chapter, first page in the 14th chapter. Here's the core concept. The night sky is filled with billions of stars, and the sun is just an ordinary star with an average brightness, and you say, how can that be? Well, the sun is really, really close to us. Now, this doesn't sound like it's really close to us, but it is. Only 93 million miles away. Okay? That sounds like a long way to me, doesn't it? But those other stars that you see out there, you don't even measure them in millions of miles or billions of miles or trillions of miles. You measure them in things called light years away, because it took the light from those stars tens of thousands of years to reach us. In fact, that star you're looking at night may not be there anymore. It may have exploded like the one on the previous slide did. Years ago, centuries ago, millennia ago, we're still seeing the light that came from it just a few 100,000 years ago, okay? It was a star back then. So it's just incredible, the distances that we're going to be dealing with. So the night sky is filled with billions of stars. Now, if you look out at night, tonight you're not going to see billions of stars. It's too cloudy. But even on the clearest night we ever get, you'll not see billions of stars, I don't think. Because you live in town, don't you? And so much light, street lights, car lights, building lights, parking lot lights, all sorts of lights, you can't see all the stars. If you were to go out in the country somewhere, way away from the nearest city, and look up at those night skies in a very clear night, you will be amazed at how many stars you'll see. You can't count them all, and that's why they say billions of stars. Okay? Now, what in the world is this picture here? We'll go over this in a minute. You'll see the same picture again, but I'll give you an idea what this is. This is a picture taken from a camera that's sitting at the base of something here. I don't know what this is, a building or something like that. But anyway, that's the North Star right there in the center of it. And what they've done is it's a very dark night. There's no lights anywhere around, way out in the boonies somewhere. And they took a camera, opened the aperture, and let it sit there all night. Or not, maybe not all night, for a while. And stars that started here moved up to here. Stars that started here moved up to here. Stars that started here moved over to there. Stars that started here moved to there. What you're seeing is the motion of the stars at night. Just like the sun rises in the east and sets in the west, the stars rise in the east and set in the west. All of them apparently going around the North Star, which hardly moves at all. Okay? We'll talk about why that's true. Those are just another flavor of what we'll be talking about in this chapter. Okay? So, let's look now at the night sky. It's too early to look at the night sky, but we'll look at it in the book. So on page 354, section 14.1, the night sky. People have been looking at the night sky ever since people have inhabited the planet. In fact, those ancient civilizations, they knew more about the night sky than we do. Now, maybe not than the greatest astronomers on Earth know, but I'm talking about you and me. Because what is it? They didn't have anything else to do. They didn't have television. They didn't have radio. They didn't have cell phones. They didn't have internet. They didn't have books. They didn't have lots of things. And when they went, laid down at night, they looked up at those skies and they started noticing things about the sky. Okay? When you look at the night sky, you'll see basically 3 different types of objects out there. They only list 2 of them here because the other one's pretty obvious. The biggest thing you'll see most nights is the moon. Now, we'll talk about the moon 2 chapters from now, so don't worry about that. That's chapter 16, okay? We're not going to worry about the moon yet. But the other things they see out there, other than the moon, in the night sky, this is after the sun's gone down, most of what they see are stars. Now, the stars at night appear as point sources. Now, what in the world do we mean by that? Well, what if you got the most powerful set of binoculars that you had, that you could lay your grubby hands on, and you looked at that star through those binoculars? You know what it looks like? It looks like a point source of light. It doesn't look much bigger than what it did when you looked at it. It may look a little brighter because you're magnifying it, but it's still a point source. If you were to get a telescope and look at that telescope, you would see a brighter point, but it still looks like a point source. That's what I was saying about that previous picture. Those little bitty points there were stars. Those bigger blobs were either something out of focus or they were galaxies. Now, we say that the little stars twinkle, twinkle. They don't, really. Most of them. They just sit there constant. What makes them appear to twinkle is that we got an entire atmosphere above us. This atmosphere goes for miles above us. And as the atmosphere changes, there's currents up there. There's some parts of the atmosphere that are very cold, some parts of the atmosphere that are ionic, some parts of the atmosphere that are all different things. As that is changing, that's what makes it look like the stars are twinkling. It's just like you're looking through, this is a really dumb example, but if you've ever been in a swimming pool and look down at your feet, they look like they're closer to you than what they really are. Well, that's because you're looking through a denser material, water, than what air is. Well, as you're looking through the atmosphere, different layers of the atmosphere are denser or less dense than other layers, so therefore it makes the stars look like they're doing something they're not. It makes it look like they twinkle. Now, here's what I was saying about the distances. Remember, I said our sun was 93 million miles away. That's approximately, let me do my math in my head here. Let's see. I'm just going to say about 160, I'm just making a guess, 160 million kilometers away. That may not be exact, but it's somewhere in that neighborhood, maybe less than 150 million kilometers away. Now, if I were to write that in scientific notation, that would be 1.5 times 10 to the 6. No, 10 to the 8 kilometers away. Okay? Well, what we're dealing with here is 9.5 times 10 to the 12th. Okay? That is, let me see if I get my numbers right, 10,000 times further away than the sun is, at least. Okay? That is what we call a light year. It's how far light travels in 1 year. Now, you may have been thinking, wait a minute, light is instantaneous. I turn on the light, the room's immediately lit. Well, that's because we're really close to that light bulb. It seems to be instantaneous. But in reality, it's not really true. Okay? The light that's coming from the sun right now, not much because it's going through all these clouds, but that left the sun several seconds ago. Several seconds ago. I don't know if you've ever noticed when they're interviewing people by satellite, say that somebody's in Kabul, Afghanistan, and we're here in the U.S. and they're interviewing, you'll see the person asks a question and the guy just stands there, or the gal stands there, and after a while they look like they're thinking, and then they answer something, and it takes a while. The reason is you're having to send that signal that goes the same speed as light up and hit a satellite and come back down to the earth over in Afghanistan. Well, that's a long trip. So it takes a few seconds of delay there. Well, guess what? The sun is several seconds old, the light before it gets here. Okay? Because light travels, here's the speed of light, 186,000 miles. Okay? 186,000 miles in 1 second. That's the speed of light. Now, how far is 186,000 miles? That would be if you stood on the equator and you were able to go around the earth, around the equator, the thickest part of the earth, go around the earth 4 and a fraction times in a single second. That would be the speed of light. Okay? That is incredibly fast. 186,000 miles per hour in a second. Multiply that by 60, and now you got 600 or 700,000 miles in a minute. No, 7 million miles in a minute. Okay, 6 or 7 million miles in a minute. Multiply that by another 60. And now you're up to 36 million miles in an hour. And then multiply that by another 24, and that's how far it travels in a day. And multiply that by 365 and a quarter, and you got how far light travels in a year. 9.5 times 10 to the 12th kilometers. That would be 9,500,000,000,000,000,000 kilometers. That's an awful long way. That's in 1 year. That's how far light travels in a year. Okay? In terms of miles, that would be about 6 with all those zeros after it. 6,000,000,000,000,000,000,000,000. That would be 3 zeros is 1,000, 6 zeros is 1,000,000, 9 zeros is 1,000,000,000, 12 zeros is 1,000,000,000,000. That would be about 6 trillion miles is how far 1 light year is. So light year is a measure of distance, not a measure of time. It's a measure of distance. About 6 trillion miles is how far light travels in a year. Okay, our sun is just a fraction of a light year away. I mean, a very small fraction of a light year away. The next closest star to us is several thousand light years away. The furthest star you could see was probably several tens of thousands of light years away. That means tens of thousands of years ago, the light that we're seeing tonight left that star. That's why I say it could be dead by now. It could have exploded by now. It could not be there right now, but we'll still see its light for 10 trillion years after it exploded. We'll never see the explosion. Someone else will, if it was just turned toward. Okay. So that's what stars are. Incredibly, incredibly long distances away. Okay? Now, what are planets? Planets are things that are much closer to us than stars, for sure, except for our sun. Three of our planets are closer than the sun. Mercury, for sure, Venus, for sure, Mars, for sure. Jupiter, maybe about the same distance or close to a little bit further. Saturn, even further. Uranus, even further. Neptune, way, way, way out there. Those are we are a planet. Earth is a planet. We go around the sun. Okay? The moon goes around us. Other planets have moons going around them. Saturn has rings going around it. We go around the sun. And guess what? The sun goes around the center of our galaxy. So everything is going round and round and round. So the planets don't give off any light. The stars are manufacturing their own light. They're having nuclear explosions constantly. Continuous nuclear explosions giving off incredible amounts of energy. Light, heat, electromagnetic radiation, very harmful radiation, giving off lots of energy. Okay? Planets, no. Planets are just sitting there. They reflect light, the planets we see, from our sun. That's all we're seeing, just like our moon. Our moon doesn't give off light. It reflects light from the sun. That's what we see. So, the planets are what we call extended sources. Now, what do we mean by that? Not point sources, extended sources. If you were to get that very high-powered set of binoculars and look at a planet, you actually see maybe not a whole sphere, but you see part of a sphere. The reason I say that, the sphere may be some of it in darkness. You're only seeing the part that's showing off light. Just like the sun, the moon looks like a circle up there, or a portion of a circle. That's what the planets would look like. The stars look like a point source. Just a source so stinking far away, you can't see any shape to it at all. Planets, for at least Mercury, if you could ever see it, I'm not sure you ever could. Venus you can, Mars you can, and Jupiter you can. Maybe on some lucky times of a cycle, you might be able to see Saturn. I'm sure you can, okay, because people have seen the rings of Saturn. Okay, Uranus and Neptune, I don't think you'll ever see. They're just too far away, and being so far away, the small, sorry, I've got to drink some water. Sorry about that. I don't mean to be advertising for newts, but someone brought that glass a long time ago. Okay. The planets are so far away, Uranus and Neptune, that their reflected light, you can't tell is being reflected. It's just too far away. All right. Now, does anyone know what that is? Can you see that picture on the slide? Anyone have a clue?
Stonehenge?
Stonehenge! Excellent, excellent. Do you know where Stonehenge is?
Great Britain.
Great Britain, you're absolutely right. Somewhere in England and Great Britain. Somewhere way out in the boonies of England and Great Britain. Now here is the fascinating thing about Stonehenge. There are so many fascinating things about Stonehenge, I don't know where to begin. First, it was built so many civilizations ago, we don't know which one did it. We know that the people currently living in England mostly came from, most recently, well, I mean, they're immigrating there all the time, but back in history as we know it, the Norman French invaded England, and that was the most recent invasion of England that was successful. Okay, they repelled Germany and all like that. That was the most successful. Before that, it was the Angles and the Saxons. The Angles, that's where they get the name England, by the way, is from the Angles. They were from some tribe in northern Europe. The Saxons were some tribe, I think German or somewhere like that. They were there before the Norman French came. And that's where we get Anglo-Saxons from. Okay? Angles and Saxons. Okay? Before them, there were some various different types of people there. Some were called Picts, P-I-C-T-S. I don't know how much is known about them, not very much, but some. There were one that started with S, and I can't remember the name of that for sure, but they were a tribe that were there. Of course, there were the descendants that the Scots came from, and the Irish came from. They were the Celtic type people. They were there before the Angles and the Saxons. And somewhere before all those civilizations, or semi-civilizations, or uncivilized people, there were the people who built Stonehenge. And we do not know how long ago and who the people were, for sure. Now, if someone can do a research paper on it and find out more information, go for it, man. I want to read it, okay? Now, here is the first fascinating thing. Well, the first one is how old these structures are. Now, originally, everything in Stonehenge was a lot like this. 2 giant columns with a stone across the top. 2 giant columns with a stone across the top. 2 giant columns with a stone across the top. You see, there's several of those still standing. There's others that are not standing. Now, whether earthquakes caused that or people came in, I don't know what happened. No one knows that either, but some of them collapsed. But of the ones still standing and the indication of where the others were standing, okay, before we get there, back off again. From everything geologists can tell us, these rocks did not come from anywhere close by in England. These rocks were brought from somewhere else. Now, I'm trying to get an idea here. And it's really hard to tell from these pictures. But uh-oh, here's somebody else trying to get in. I can't see who it is. Can you see? It may be Parisha again. I couldn't tell. I got something that pops up on my screen every now and then and blocks things out. Okay, these stones came from, I believe if I remember correctly, thousands of miles away. Now I'm going to try to point out something here. I'm just making a guess here. Here's a guess. You see this rock that's fallen down here. Okay, the height of that is approximately, I'm thinking around a man's height, about 6 feet tall, maybe taller. So these things are huge. They're incredibly huge. Okay, these rocks were all brought from thousands of miles away. First question, how did an ancient civilization, now here's something in the background here. These are probably, now they're a long way away, but these are probably cars or things somewhere way out there. They could be animals, I don't think they are. But, oh, right over here, I bet you that's a car back there. That shows you how big, or a truck or something like that. These things are huge, okay? How in the world did a civilization that ancient ever transport this many stones for such long distances? Number one, how did they do it? Why did they choose those stones? Why didn't they use stones from the area? Nobody knows. Okay? So there's another mystery of Stonehenge. Who built it? We don't know. How did they get the materials here? We know they weren't native to the area. How did they get them there? We don't know. Now next, how did they get them to stand like this, and how did they get these rocks laid across the top? Because those things weigh, I'm guessing, hundreds of tons. How did an ancient civilization build this Stonehenge? Okay? Another mystery. Now here's the thing that taps them all. If you were to get, I can't get my cursor, there it is, and go in the center of Stonehenge, and you were to look out at night from the center of Stonehenge, you would see a certain star or constellation that would come up in any one of these gaps in between here at very specific times. These stones were not only huge, not only put in place, but put precisely in place to mark, basically as a calendar or as a recorder of the day of the year, month of the year, season of the year. They told these ancient civilizations way more than we can ever imagine. Maybe the sun rose at a certain time through one of those things, and they knew exactly when there it was. I don't know how many pairs they were. I'm guessing 12. Just making a guess here. 1, 2, 3. Yes.
Is it like a clock?
It's like a clock, only it's the biggest clock you could ever imagine. Okay? But not only a clock, it's a clock that measures years, seasons, months. It measures everything. Okay? Incredible. And it's that precise. You can still see those events happening just like they planned them to happen. How did they do that? How did they have the technology to do it? How did they get them so precisely located? It's a mystery upon mystery to me. Stonehenge. Okay, I can't get screen to, there we go. So let's move on to what they're calling the celestial sphere. Okay, I'm trying to find this in the book. Oh, here it is. This is also, Stonehenge picture was on page 355, or it may be 14.3. Back on 14.2, we're going to talk about the celestial sphere. Now, this is a man-made construct. It's not really a sphere, it's an imagined sphere. And it's basically how the ancients looked at things. When you laid down on the ground at night and looked up into the heavens, you saw all the stars up there. Now, it wasn't hard to imagine that somewhere up there someone had put a great big old bowl and had put all these stars somewhere on that bowl. Only it's not really a bowl, it's a sphere, because that sphere is revolving around the earth. Turning around the earth, because those stars are indeed moving. Okay? If you looked at them at night before you went to sleep and then found the same one the next morning, it was traveled across the sky. In fact, you may not even be able to find that star because it traveled completely across the sky, because that celestial sphere seems to be revolving around the earth. So basically what it does is projects the celestial objects, those stars, possibly the planets, okay, other things like that, onto an imaginary sphere that completely surrounds the earth. That's what they call the celestial sphere. Celestial meaning star. Now, if you imagine, and let's see if I can get a slide to show this. Yes, that here's the earth in the middle of that celestial sphere. Here's the celestial sphere out here with all those stars planted on it. Now, we know this isn't what really is happening, but this is how they originally viewed it. So let's just imagine that you had a light that was at the center of the earth, a point source of light, and that you really did have an equator that was really a line that went around the earth, right like this, an equator, and that light inside showed a shadow where the equator was. That shadow would then be what we call the celestial sphere. The celestial equator, sorry, celestial equator. And that's what this line here is. That would be a projection of our equator out onto that celestial sphere which is surrounding the Earth. Now, just as we have a North Pole up here, then you'd have a celestial North Pole right above it. We have a South Pole down here, you would have a celestial South Pole down here, right below it. Okay, and anywhere you are on the Earth, there would be some object that would be, you could reference the stars according to the celestial sphere, just like we reference where you are on the Earth by latitude and longitude. I'm not sure if you're familiar with that, but that's what we do. So we have the Earth with poles on either end, okay, an equator that's, and by the way, you know what the word equator means? It sounds like the word equal, doesn't it? It's equal distance between the North and the South poles. Equator, equal distance between the poles. And that's exactly what the equator is. So the celestial equator is exactly equal distance between the North Celestial Pole and the South Celestial Pole. Okay? So that's your celestial sphere. We'll be referring to things on the celestial sphere. Okay. Cormisha is in the waiting room again. So let's let her back in. Okay. Now, there seems to be, my slide is not working again. Okay, there's celestial sphere. Now, there seems like there's supposed to be a picture here, and if you do happen to have your text, it could be a picture of a person standing on the surface of the Earth looking at a star. Let's see if that picture shows up anywhere else. No. Here's that next picture. This one I think you'll recognize. This is a picture of a night sky taken with a camera who you left the aperture open for several hours. So that this star, if I could get it again, would have moved from here to here, this star from here to here, that star from there to there, that star there, all going the same, approximately the same distance, or angular distance anyway. So you left it open for several hours at night, and you created this. Why the North Star doesn't seem to move? That's because the North Star is directly above, on the celestial sphere, above our North Pole. And you see those stars aren't really moving. It's the Earth is spinning on our axis down here. The stars are fixed in space. In other words, that celestial sphere is stationary. We're spinning inside, and that makes it look like the stars are moving around the North Star because they are spinning around like this. Some are spinning further away, some are spinning very close. And that's why the North Star appears to sit right where it is. And those stars moving close to it are moving around in the small circles, further away, and further away. Okay, objects appear. Okay, so let's talk about a couple of things here. First, the altitude angle. And then we'll talk about the azimuth angle. These determine the locations on the celestial sphere. Let's see if we can get a graphic that illustrates it. Ah, here it is. There's the guy standing there. Okay, now here's the guy standing on the surface of the Earth. Here's the celestial sphere up here. It's an imaginary sphere above him. Let's say he's looking at this star here. That star, from his horizon, which is horizontal to him, goes up a certain angle. That's 30 degrees up. So that's called his altitude angle of that star. From the sky's horizon, how many degrees up the celestial sphere, that shows. That's a 30-degree celestial angle. Now, that's like our latitude lines are on the globe, if you're familiar with that. Now, how do you measure where you are from where? Well, you take 0 degrees to be true north, 180 degrees to be true south. So measure in the clockwise direction from due south, or measure east from due south, how many degrees it is from due south. That's 45 degrees east of due south. that's called the azimuth angle. Okay? Now, don't get too bent out of shape about this, but this is how we would identify that star. It's so many degrees east of due south and 45 degrees east of due south and 30 degrees north of the horizon. That identifies exactly where that star is for that person. Now, some person over in another country or somewhere else, they look at the star and it's going to be different, okay? But for this person, for where he is, standing right there, 45 degrees east of due south, 30 degrees north of his horizon. Okay. Now, since we have the guy standing here, if he were to turn and face due north, and then look from due north directly overhead, and then twist his head all the way around and look at due south, you have just defined his celestial meridian. That's his meridian on the celestial sphere. The point directly overhead is called his zenith. They don't mention it here, but it's Z-E-N-I-T-H, his zenith. That would be directly overhead on his celestial meridian. Okay? And then on the meridian where this star is, that meridian would be 45 degrees east of due south. That would be the azimuth angle. And then going up that meridian would be 30 degrees north from his horizon. Okay? So that's how that guy would locate that star at that moment. Okay? So that's how we use the celestial sphere, or one simple way of using it. Okay? Now, that moves us into section 14.2 on the slide set. Before we go there, I just wanted to point out a few things, features that this book does. There are a few other figures in the book that maybe were in the places where there were blanks there. I don't know. But this is a figure of an object probably all of you will recognize. Do you see that one that shows the Big Dipper going around the sun? Am I holding it in the right place?
Yes.
Okay, can you see that? I'm just guessing at it because I can't see. Do you see that figure? Yes?
Pull it out just a little bit.
Do what? Down?
Okay, now you're almost perfect.
All right, good deal. Okay. At different times of the night, the Big Dipper is dipping in different directions. Okay? And that's because it's revolving around the sun. I mean, the Earth is revolving around its axis, and it makes the stars appear to move. And that set of stars that makes what we call the Big Dipper, that's not really a constellation, it's given a different name.
Whenever you look that way, we can't hear you. It's kind of muffled.
What's that again?
Whenever you look that way,
Right?
it kind of muffles the sound.
Okay.
As well.
Okay, I couldn't quite make out what you're saying. I'm hard of hearing, so get a little.
Now we can't hear anything.
Say again?
Just a few moments ago when Roy was talking to you, we couldn't hear anything. It was like you started mumbling and then it's like it went silent. We couldn't hear anything. We could see your head moving like you were talking.
So Roy, if you could get either closer to your microphone or I don't know if turning your volume up will work or not. Yeah. Say,
I couldn't hear you.
Say again?
I couldn't hear you.
Oh, you can't hear me.
Right.
Yes.
Maybe you like look over one direction. We couldn't hear you.
Yeah. Like
Okay.
you turned your head that
Okay,
direction.
you're talking about me then. Okay.
Yeah.
Oh, I thought you were talking about Roy. Okay, when I turn this way, you can't hear? Okay.
Yes,
Yes,
I'm going to make a solid sound. Ah. Did that change?
yes, when you turned, it changed.
It changed. Okay. I'll try to face most of the time, but the book I can't have right in front of me, so I periodically will look at the book. Okay. But you could see the Big Dipper going around the North Star, right? Can you hear me when I say that? Because I'm behind the book then.
Yes, we can hear you.
You could, okay. All right. Now, the Big Dipper is not really a constellation. It's part of a bigger constellation. By the way, the name of it is the Big Bear, or Ursa Major. The Big Dipper is just part of that, okay? It just looks like a dipper, so we call it that, okay? It's probably just about the easiest thing to pick out of the night sky. It's usually not too far from the North Star, and here's why. Here's a concept supplied. Once you get your book, I won't have to be holding these up, but can you see that concept supplied?
Okay, you're going in and out. We can't hear you now.
Okay, can you see the concepts applied in the book?
We still can't hear you.
You can't hear me at all. Okay, I'm facing the thing. What I'm guessing is I must have a weak signal. Say that again? No, I'm talking beside the book now. Is this any better?
We can't hear you.
You can't hear me at all.
Mm-mm.
Well, you heard me say something. You said, okay. I'm beside the book, so
All the time, we can't hear you.
You're not hearing me right now?
No.
Okay.
It's going in and out with the book right there.
Okay, but I'm beside the book. I'm not, see, I'm beside the book. I'm not
It's better when you move beside the book.
Okay, but I'm beside the book right now. But this
now is perfect.
Okay.
Just like that.
Wow. I don't know where my microphone is, but it must be right here in the center.
Right by the camera, probably.
Okay. Let's try a few things. Is it louder here or is it louder down here?
Try that again.
Okay, I'm talking to the top of my computer. I'm talking to the bottom of my computer.
The bottom.
The bottom is louder.
What do you think, Roy?
I think the bottom, but if you look to the left or right.
Yeah, okay, I understand that. Okay, so here's what I'm going to try to do when I'm holding the book up. I'm going to try to get under it. Can you hear me now?
Perfect.
Is that better?
Much better.
Okay. Can you see the... Oh, wait, okay. Here's the concepts applied here. Can you see that?
Yes, sir.
Okay. Now, you see the Big Dipper is the one further away. It's a very clear Big Dipper. You can see that. The two outermost stars on the scoop of the Dipper, those are called the Pointer stars. Not the Pointer Sisters, that's something else. Okay, the Pointer stars. Okay, and those Pointer stars point to the North Star. Now, the North Star is the very end star on what they call the Little Dipper. And even on a really clear night out in the country, I can barely make out the Little Dipper. Big Dipper is so easy to find, but you can point those and look to the north and you'll see the North Star. And then you look very hard and you can kind of make out the Little Dipper. The handle turns in a different direction. It's sort of weird, but that's actually part of another constellation called the Little Bear, okay? Ursa Minor, okay? Ursa Minor. Now, so I was showing you that because the book does have some of these concepts applied that really give you a lot more information. It's usually pretty interesting information. Now, I'm going to show you something else. Do you see this? It's entitled Myths, Mistakes, and Misunderstandings. Can you see that one? It's sort of a purple block, okay? Those are really interesting some of the times. Other times I think they're really lame. But this one is just talking about the rumors that you hear that you might be able to see stars in the middle of a day if you look into a well. No, you can't. I've heard it said if you had a long enough tube, like a tube that paper towels come on, if you had a real long one, you could look out and just block the sun with that and you could see stars. No, you can't. Okay? Those are mistakes, misunderstandings. Okay? Now, here's something that is true, though. If you look out the sky right now, I can look out my window. It's pretty gray looking because it's raining. Do you know that there's billions of stars out there where I'm looking? You can't see them because the sun is so close, so bright, that it's interfering with seeing any of those stars. Just like street lights and building lights and parking lights and city lights block us from seeing those tiny little stars out there, the sun blocks every one of them. In fact, the moon may be up right now, but the odds are if it is, you can't see it either because the sunlight is so bright you can't. Every now and then you will see the moon in the daytime, just a fraction of the moon. All right. So now we're moving to 14.2. This is on page 356 in your book or page 14.4. We've gone a big 4 pages into the text. Okay? This is the stars. Get the idea of what the stars are. Now, if I sit back in my chair, can you still hear me okay? Okay. Now, the stars are massive. What we mean by massive, they have a lot of material in them. Enormous amount of materials. Very dense, meaning really packed in there. Balls of incandescent gas. Now, what does incandescent mean? It's giving off light. That's why we call it incandescent light bulb. It's a bulb that's giving off light. Incandescent gas. So basically what a star is, a great big massive ball of gas. Now, when it says dense, it's nothing dense like a rock or dense like water or dense like anything else, but it's still, for a gas, incredibly dense. Okay? So dense that those molecules rubbing into each other are creating heat. Now, that's not the main source of heat, but they are close enough to create heat. Now, why are they incandescent? Why are they giving off light, these masses of gases? That's because somewhere in the core, the very core of that star, which is the very fairly small innermost part of the star, you have, that's the core, that is so hot, so dense, that you have nuclear fusion occurring. Now, what nuclear fusion is hydrogen atoms being forced so close together with such intense strength that they're fusing into helium. Okay? Now, that may not make any sense to you because I meant to say this earlier, so that's going to be a little time out here. Okay. This is a book on physical science. Okay? If you were to look at the table of contents of this book, the first half of the book is physics and chemistry. The last half of the book is earth science, meteorology, and oceanography. Okay? Astronomy and earth science. Astronomy and earth science. Okay? That's how the book is put together. As if you had already read the physics and chemistry parts before you ever get to the astronomy or earth science parts. Now, why do I mention that? Because a lot of what they're talking about here is assuming that you've already had the physics and chemistry parts. Well, of course, most of you have not. Capri had a little bit of the physics part, but when we went off campus, she couldn't continue. So she only had a little bit of that. We only did a little bit of the chemistry part. But see, the state of Alabama, I guess, assumed that astronomy and earth science was easier than physics and chemistry, so they put Physical Science 111 to be the first course and 112 to be the second course, but the book is written as if you had already had the first half before you got to the second half. But we do the second half first, so sorry about that. State of Alabama, thank you very much. Okay, but This is assuming you know what this is talking about. So I'll try to fill you in on that. First, sort of the chemistry of it. Okay? If you do get the big book or have the big book, that last page in it, can you see that? It's called the periodic table. Okay? This shows all the elements that we know of. Maybe not holding it well. The first one over here is hydrogen. That's the very lightest element there is. 1 proton, no neutrons, 1 electron. That's all there is to hydrogen. Helium over here is the second lightest. It has 2 protons, usually 2 neutrons, and 2 electrons. So it's about 4 times as massive as hydrogen. Okay? So what you have is hydrogen being forced together with such incredible forces at such incredible temperatures that it's fusing into helium. And when that happens, enormous amounts of energies are given up. Incredible amounts of energy. And that's why the sun is heating us up. When we're 93 million miles away, the sun is still providing enough heat to keep us warm. Okay? And then it's sending out that much heat into all the rest of space, and only a few planets pick up any of it. The rest of them are just seen by other stars, if they have anyone to see them. So that's what we mean, powered by fusion reactions at their core. Now, some of the bigger stars, and we'll talk about this later, actually have bigger reactions going on, like helium fusing into carbon, or carbon fusing into something else that ultimately fuses into iron. That's what's going on in those supernovas that I was talking about when a star is exploding. We'll get there later. Now, our sun is just an average star. It may look bigger, much, much bigger than all the other stars. It may look much, much brighter than all the other stars, but in reality, it's just an average star. It's about medium size, medium brightness, medium everything. It's just an average star. But it's what we use for reference for understanding other stars, because it's right in the middle of the scale. There's stars that are much weaker and dimmer and cooler, everything, and there's stars that are much bigger and hotter and stronger and brighter, okay? Our sun is right in the middle. Now, where did these stars begin? Well, you might think that outer space is completely empty, void, is nothing but a vacuum. And it almost is, but not quite. Because most of the space has very randomly, every now and then, an atom or two of a gas in it. Just way out there. But sometimes you have masses of gases that start accumulating. And that's called a gaseous nebula. Now, I don't know if you've heard of the term, oh, that's pretty nebulous, which means it doesn't have much form or structure to it. Well, that's what a nebula is. It's just a cloud of gases. They're very far apart. They are very huge, taking up enormous areas of space, volumes of space. In fact, our whole solar system could fit in some of these gaseous nebula. Okay, incredibly large amounts, but very spaced around. Now, those gases are mostly hydrogen. Now, I can't tell you why they're mostly hydrogen, but they are. The simplest gas that there is. 1 proton, 1 electron, no neutrons. Mostly hydrogen. Okay? Now, if that mass of gases is out there, okay, somewhere out there in space, and some shock wave comes through. Well, why in the world would a shock wave come through? Well, remember that figure that we saw early on that I said was a planetary nebula? That was a huge star that had exploded. Well, that's going to form a shock wave, okay? And that shock wave comes along, maybe has been traveling for hundreds of millions of miles, and that shock wave comes along and pushes some of these gases closer together. Okay? Now, when these gases move closer together, now gravitational energy is released into higher temperatures and pressures. Now again, this is assuming you've had chapter 3 or 4, 3 back in the first part of the book. We haven't had it, so let me try to explain what's going on. If you have a bunch of gases here, they're far, far apart, only occasionally will they ever collide with each other and they just bounce off and go. But now the shock wave has made them get closer together. Now they're bumping into each other with more frequency. They are maybe traveling a little faster because of that shock wave. They have more energy. Now, as they collide with each other, the friction, even of gases, hydrogen gas, produces friction, and friction produces heat. Now, I want you to take your hands, put them together. I'm not going to have you pray right now, but I want you to rub them together, back and forth like this, really hard, pushing them together. What do you notice? They heat up? Yes, that's because of friction. Same thing happens when these masses of gases get pushed closer together. They start heating up because of friction between the molecules. That's what we saw. The gravitational energy, as they come together, become higher temperatures and, of course, higher pressures. Now, what are pressures? This is assuming you've already had the earlier chapter. Pressure is force per unit area. If you've ever measured the air in your tires, you say it's about 32 psi. What is a P? Pound. What's a SI? Square inch. PSI is pounds per square inch. Force per unit area. Square inch is an area, pound is a force. Okay? So they start increasing pressures, increasing temperatures, increasing pressure. Okay, guess what? As they get closer together, they got more mass concentrated in a smaller area. This bigger mass starts pulling in other atoms, other gases. So this accumulation of gas, I can't get this thing out of the way here. I'm waiting for it to do. I don't know why this block gets right in my screen. You probably can't see it right here. It says, please move this window away. There's no window there. Okay. Now this is forming what they call a protostar. This protostar is not yet a star. Think of that as a pre-star, a protostar, before the star. It's now an accumulation of gases that will become a star. When it's that gaseous nebula there, that may or may not ever become a star. But now when those gases start collecting and getting closer together, and now get bigger masses and start pulling in other gases, and now at some point it gets to the place that the gases can't escape. And there's enough of them there that ultimately this is going to become a star. Not going to be immediate, but it will happen. Okay? That gets us to the protostar stage. Okay? Now, they're going to stop right there, okay, in the origin of the stars and start talking about some other things. Now, once you get your book, they introduce example 14.1. We're not going to do it, but this is just going to give you an idea of some of the sizes we're talking about. Okay? Now, I'm going to try to keep the book in front of me so I won't turn my head as much. The Orion Nebula. Now, I don't know if you know what we're talking about there. After the Big Dipper, the next easiest thing to me to recognize in the sky at night is the constellation called Orion. Now, I can look around the Big Dipper and try to see a bear, and I'll never see a bear. And I'll look around the Little Dipper if I can ever find it, and I'll never see a little bear. Okay? Those constellations, I'll never know how they made those out, except they're just lying there on the ground saying, hey, that sort of looks, like you look at a cloud, you say, hey, that cloud looks like an elephant. And I'll look at it and say, it does? Okay, well, somebody looked at that and said, that looks like a bear, and they named it Ursa Major or Ursa Minor. Well, there is one constellation out there that really does look like a warrior. That's the constellation Orion. Now, Orion looks like it has a big shield in front of it. It looks like he has a belt around the waist. It looks like he has a sword in the belt. If you know where to look, you'll see that. And maybe in one of the labs we can look at some of these constellations and pick them out. I don't know. I haven't found them yet, but I'm going to try. Okay? So that constellation called Orion, it's not usually anywhere close to the Big Dipper, but it's usually, in another part of the sky, and it really does look like a shield, a belt, and a thing. And you can almost see the shoulders and the legs almost of a warrior. I can't see a warrior, I can't see a head or anything, but you can sort of pick that out. It's a huge constellation. That Orion Nebula that's in that constellation, that's a mass of gases, is about 20 light years across. 20 light years across. Remember, a light year was so many trillions of miles, and this is 20 trillions of miles across, enclosing roughly a spherical area with a volume of about 4.19 times 10 to the 57 square centimeters. Now, I can't even picture how big that is. But what I'm getting at, that is a huge mass of gases. Now, they tell us here, if you were to calculate the number of sunlight stars that could conceivably be built out of that big mass of gases, they do the calculations here, and we're not going to do them. It comes out to about 4,000 stars. So you would get about 4,000 plus suns out of that one massive nebulous of gases. Of course, it will probably never form 4,000 stars, the size of our sun. But at some point, it'll probably make a few stars. Some of them could be huge, some of them could be small. It may make a few hundred or even a few thousand stars. We don't know, but the mass of gases is there. But that's just to give you an idea of what volumes, what distances we're talking about that those masses of gases are in. Okay. Now, here is a picture of that Orion Nebula. Can you see that? Am I holding it in a place where you can see it?
Down a little.
Down a little?
Little more.
Little more?
Little more.
Little more?
Perfect.
Perfect. Okay, I'm blocking most of my access to the microphone. Can you still hear me?
Yes.
Okay, well, I'm talking beneath the book, so hopefully that'll work. Okay, so that's the Orion Nebula, a picture from the Hubble Space Telescope, I'm sure, of that.
Okay, now we can't hear you.
Okay, I had to turn my head. Let me hold it this way. It's hard to really read. Okay. No, actually, yeah, that probably was that. So that's a huge, huge, huge mass of gases. And the Hubble Space Telescope and others like it can take that. All right. Now, what we did on the last slide was talk about where stars start. Now we're going to stop and talk about how stars are put together, which is a weird way to do this, but this is how the book's doing it. At the end, hopefully it'll all make sense. Okay? So what we're doing is we talked about how they began as a mass of gases that surge of something or another that forced them together. They become a protostar. We're going to stop right there with the protostar. Now, we're going to look at how the stars are put together. At the very center of the star, we said this earlier, is the core. You talk about hot. Very, very, very hot. It's the most dense region, so you have the most friction, but not only the most friction, the most pressure, the most highest temperature, so much so that nuclear fusion is forced to happen, and that nuclear fusion releases this incredibly strong radiation. Gamma radiation is the strongest of the radiations. If you were to be exposed to gamma radiation, very much of it, depends on how strong a dosage, you're either going to die instantly or you're going to die a very slow, painful death. I mean, gamma radiation destroys tissue. X radiation is not quite as strong as gamma, okay, but it's still pretty deadly. And you might say, hey, wait a minute, I've had X-rays. You've only had them for very low dosage, very short periods of time. If you've ever had an X-ray, they just zoom it for just a little bit. But if you've ever noticed what those technicians are doing when you're getting the X-ray, they leave the room because there's enough radiation there. If they were to stay in the room, every time they did an X-ray, they would accumulate enough radiation, it would damage tissue. So they go into a different room with a thick, dark window in it. That's a leaded window, and I'm talking about a thick leaded window. And that wall between you and them, that wall has lead in between the walls, okay? That is blocking every bit of that radiation they can do from getting to you. They're seeing what the X-ray is doing. They're not being exposed to it. They're wearing badges. Those badges will be exposed over time. If they turn in their badge and 1 month they get too much radiation, they're out of work then for another month or two until they get their radiation count slow. That's why they stay out of the room. So that's what's at the core. Nuclear fusion. That's the only place you have nuclear fusion, and that is intense. Incredibly, incredibly hot. We'll talk about the heat later. Okay? Outside of that, they have what they call their radiation zone. So here's the core. That's, if I can get there it is. The core is really small compared to the whole star, and that's where all the nuclear fusion is happening, in the core. Here's the radiation zone, and that's what is being shown here. The radiation is moving outward from the core to the outer parts. That's the radiation zone. The radiation diffuses outward over millions of years. Now that, I don't know exactly what they're talking about. The radiation moves at the speed of light, so it doesn't take it that long to get out, but it means it just keeps coming from there over millions, and in some cases, billions of years. Okay, we'll talk about the time later. Okay, the convection zone, that's the outermost part here. The radiation is always leaving from the core and moving outward, but at some point out here, when the radiation begins to lose a little bit of its energy, then the higher energy radiation is moving out. The radiation that's lost energy is moving in. That's what we mean by convection. Okay? Now, this sounds like a dumb question to ask at this point, but have you ever seen the old cookware that they named Visionware? It was basically pots and pans made out of glass.
Yes.
Sort of amber colored, sometimes blue or something like that. Okay, if you can imagine one of those on the stovetop, pretty much filled with water, you turn on the heat underneath it, you would actually see, after a while, you would see bubbles going up from the center, going around the top, and coming back down the sides. That's convection. The hottest water is moving up in the center because it's less dense, and the cooler, it cools at the surface, moves around, becomes more dense, and moves back around the sides because the sides are cooler. And that's called convection. That's exactly what we have going on here. The radiation is moving up as the hotter radiation is moving up, cooling off, coming back down. This is the convection zone. That's the outermost skin or surface of the star. The star really doesn't have a surface because it's all a gas. It's a mass of gases. But the outermost layer, that's why it has the spherical shape around there, because that's the convection zone. It's structured from hot material, gases, rising from the interior, cooling, and then sinking back again. And that's what's happening constantly around that star. The upper reaches, that's what we call the visible surface of the star. even though it really doesn't have a surface. It's just the outermost layer. Now, our sun, an average star, that its surface temperature is about 5,800 Kelvin. Now you might say, what's a Kelvin? Well, a Kelvin is a unit of temperature that's the same size as a degree Celsius. It's just started at a different level. Okay, if you were to go outside now, I'm guessing it's right around 70 degrees, and probably that in your house too, wouldn't you say? Somewhere close to 70, okay? That would be about 20 degrees Celsius. Fairly close. 68 Fahrenheit is 20 Celsius. And that's about what it is outside and in my home right now. Somewhere around there, about 20 degrees Celsius. We'll add 273 degrees to that, to 28, and you get awfully close to 300. Okay, let's just say around 300 Kelvin. That's the temperature in your house right now, 300 Kelvin. Okay, now the difference between that and the boiling point of water would be another 80 degrees Kelvin. So 80 K, I said it wrong there. You never say degrees with Kelvin, another 80 Kelvin. So 80 Kelvin is the difference between the temperature you are now and boiling water. That's 80 Kelvin. Okay. So add to that 300 K, another 5,500 K, and how many times is that the difference in the temperature of water? Oh boy, that's hot. That is incredibly, incredibly hot. And that's an average surface temperature of a star. Not too hot, not too cold, just about average. Many stars are way hotter than that, and many stars are a lot cooler than that. But that's our sun, pretty close to the average temperature of the star. Is that anything close to the temperature at the core? Nowhere close. Temperature at the core is so many times greater than that, it's unbelievable. But 5,800, about 6,000 K, is the average surface temperature of our sun and of the average star. Okay. Now, there is another figure in the book that's not on our slide set, and I'll show it to you now, but I can't read the text to you because I'm showing. Can you see that? It looks a little like the one there, but it's different colors. It's reds and oranges and yellows. Can you see that? Am I holding it right?
Yes.
Okay. So sort of get a grip of what that picture looks like, and then I'll set the book down and explain what those features are. Again, that light yellow part in the center, that was the core. Okay, that's where all the nuclear reactions going on. What's that? Okay, I'll turn my head again. Yes. Okay. That yellow part in the center is the core, and then the sort of darker yellow going out. Okay, somebody's going out and come in again. Let me admit them. I can't see who it is because the stinking thing is in the way.
I think that was Portia, maybe.
Okay.
No, she's here.
Parisha?
No, she's there.
Okay. Well, she came back in. So whoever it was, I admitted them back in. Okay. Now, so trying to describe this, I'll try to point out to you on this one what I'm seeing on the other one. Here's the core. That's, like I said before, that's where all the nuclear reaction is going on. Okay? This is the radiation zone here. That's where the radiation is leaving from the core and moving toward the surface. Okay? That's where most of the energy transfer is happening. I can't, cursor goes away at times. And then the convection zone carries the energy outward, and some of it escapes, some of it is circled back in. Okay? So it's not a lot new, but it's showing approximately the distances. About 25% or a quarter of the radius is from the center of the core to the outer part of the core. Between 25% and 70% gets to the through the radiation zone, and 70% to 100% is the convection zone. That's the only thing new that this figure showed that the previous did not. Okay, now let's move on to the next slide. Okay, so they started telling you how the star begins. Then they jumped into how the star is structured. Now we're looking at the lifetime of, say, our sun, which would be similar to any star. Okay? Now, if you're following in the book, this is not following the book too closely. Our book takes a different approach. He rearranged the chapters in between the time he sent out these slides and he put together the new edition of the book. So we're going to come back and talk about the brightness of the stars, the star temperature, and star types. We'll come back to that. We're going to jump over to page 361, and this is the life of a star. Okay? We're going to take our sun, but you can extend this to any star. Now, here's our sun, an average star. Okay? Average. Bigger stars, going to produce a lot more. Smaller stars, weaker stars, a lot less. It converts. Now, when it says convert here, I want to remind you, this is where I really miss my ionizing pen. Now, I'm going to do something here, and it's not going to be very pleasant, but I'm going to do it. Can you see the whiteboard here? Can you see the whiteboard?
Yes, sir.
Okay. Now I'm going to try to write on the whiteboard. Okay. I think you'll recognize this equation. E is equal to, anyone want to make a guess?
MC squared.
You got it. MC. Now I can't do a square with this computer. So what I'm going to have to do is do a caret key. That means what follows that is supposed to be. That's supposed to be C squared. Okay? Einstein's famous formula, right? Okay? Now what does this say? This is saying the M here stands for mass. If you are taking a tiny, tiny, tiny amount of matter, let's just say a gram or two, that would be about an aspirin tablet or two, okay? Multiply that mass by the speed of light. Remember, 186,000 miles per second, okay? Square that number. Just think how big that number is. 186,000 miles per second is almost 200,000 miles per second. That'd be 2 times 10 to the 5th. Square it, that would be close to 4 times 10 to the 10th. Okay? That would be 40,000,000,000, huge number. 440 billion, I think it is. Yeah, 40 billion. Take that, multiply it by that mass. That's how much energy you produce when you convert mass to energy. A little bit of mass is going to make an enormous amount of energy. Well, here's what the sun's doing. Okay? Going to close this out for now. Get my, if I can get my cursor to show up. It goes everywhere but where I want it to. Okay, there it is. Okay. You can see the PowerPoint again?
No,
yep.
We see you.
Uh-oh. So that means I've lost the cursor again. I mean, lost the screen again. Okay. Oh, yuck. No, that won't work. Okay, let me do this. Okay, that's not really what I wanted to do, but it works. Let me get back into the meeting. Okay, now you can see me again, right? Go back to PowerPoint. Okay, and go back.
Now we see the PowerPoint.
You can now?
Yes, sir.
Okay, and they go back to the current slide. This is really awkward having to teach this way, but it's the best we got. Okay, so here's the lifetime of the sun. It converts about 1.4 times 10 to the 17 kilograms of matter. Now this big old book that I have here is about, I'm guessing, about maybe 2 kilograms, maybe less, maybe 1 kilogram. Okay, let's just imagine we had 1.4, or let's say 140, 0,000, 000, 000, 000, 000, something like that, of these books. Okay, that's how many you had. That's how much of the sun's mass is being converted by Einstein's formula, E is equal to mc squared. Just think about how much mass this is multiplied by the speed of light squared. That's how much energy. Okay, that's about 2,700 3-ton SUVs are being converted to energy of the sun every year. That's how much hydrogen is being lost when it combines with to form helium. That's how much of that is being converted to straight to energy. Okay? Now the sun has been doing this for about 5 billion years. And all of the scientists' estimates, by measuring how much hydrogen they can see still in existence on the sun, figure the sun has about enough hydrogen for another 5 billion years of fusion. Okay? Now, I don't think I have to worry about being alive when it runs out of gas. Okay? Not me. Okay? I'm not going to worry about that at all. So not only do we have an average sun, but it's about midway through its life. So it's right at its midlife crisis here. Okay? So I'm going to get this thing out of the way. It keeps popping up. You can't see it, but it's in my way. Okay. Now, the lifetime of any old star depends on how massive the star is. Now, I want you to make a guess without looking at here. Would you think a bigger star has a longer lifetime or a shorter lifetime?
Bigger has a.
You would think a bigger star would have a longer lifetime. Not so. Even though there's a lot more mass there, the thing is, it's burning it up so much faster. The less massive stars have the longer lifetimes. The more massive stars have the shorter lifetime. Now I'm going to go to the book again, try to hold it in front of me so you can still hear me. I'm wanting to make sure I got this right, and I don't see it immediately here. But I'm going to go from my memory here. Our star, an average sun like us, we're in the neighborhood of 10 billion years will be its lifetime. The less massive star you measure in trillions of years, not billions of years. The more massive stars, the huge, most massive stars, they are only measured in millions of years. Okay? So our sun, being right in the middle, is going to be about 10 billion years. The bigger stars are only in a few millions of years, hundreds of millions of years. The less massive stars can last trillions of years. Okay? So, big differences there. Now, because I did something, I can't get my cursor to work. Now I can. Okay. So, let's go backwards a moment here, back to page 358, and we're going to talk about the brightness of stars. Now, there's a lot of ways to talk about the brightness of stars. One of these ways is what we say the obvious brightness, okay, stellar brightness. We call that the magnitude, the apparent magnitude, okay? Now, here's what's going to make differences in stellar brightness. How much light is that star really producing? Okay, our sun produces an average amount of light because it's an average star. The huge stars are going to produce a lot more light, okay? But the very tiny stars are going to produce a lot less light. So the amount of light produced. But then you also have the size of stars. Now, when I'm saying huge here, I mean more massive stars produce a lot more light. Less massive stars, less light. But some stars, even though they're very massive, might not be all that big in size because they may be a normal star. A star that's getting ready or is already in the process of exploding, it may be huge in size but not that massive. So that's what we mean by size of star. How much volume does it take up? The amount of light produced depends on how much mass the star has. But the other one is the distance to the star. We're so close to the sun, it completely outshadows every other star in the sky. Okay, so it's only when the sun's on the other side of the earth from us can we see those other stars. But then the ones that look bright may be just because they're close to us. They may not be that big or they may not be that massive. But then on the other hand, some that are very bright could be very massive and average size, but a long way away. Okay, so you see, all these factors go into what we see or perceive of the brightness. And that's what we call apparent magnitude. Now, they had to come up with some scheme to quantify that brightness. So the first magnitude stars are about 100 times brighter than the sixth magnitude stars. Okay? Now these are the ones, the stars that we typically see. So there's 5 uniform divisions in between. First magnitude stars, the very brightest, and then second magnitude stars, third magnitude stars, fourth magnitude stars, fifth magnitude stars, and sixth magnitude stars. 5 divisions in between the brightest to the dimmest that we can see. Okay? And they're fairly uniform in the divisions in between. And here's what that looks like on a scale. Okay? This is apparent magnitude. Okay? And remember, we're talking about stars, not planets, not moons, not our sun, the other stars. The brightest star out there is one named Sirius. The brightest star in our night sky is Sirius. That's a 6 magnitude star, which on this scale is listed as a 0. Okay? Now, look at this. Jupiter, when it's at its very brightest, is quite a bit brighter than Sirius, the brightest star out there. But of course, Jupiter's a planet. It's just reflecting light from the sun. The brightest Venus, which is our closest planet neighbor, is even brighter than that. It's about, I can't get the cursor back. There it is. That's about 4 magnitudes brighter than Sirius. And Venus, because it's the brightest thing out there, except for the moon. The full moon is brighter than Venus by a long shot. And the sun, of course, is so bright it blocks out everything, except occasionally you'll see a moon when the sun is shining, but that's all. You won't see any star. So the brightest Venus, that's the first object you'll see at night other than the moon, and that's because it's the brightest thing out there. So it's often called the morning star or the evening star because it's the first thing you see in the evening, the last thing you see at night, in the morning. The last star to disappear in the morning. It's not really a star, it's a planet, Venus. Okay? But of the stars, Sirius is the brightest. It would be the first magnitude, the brightest one. Okay? Now, the dimmest one that you can see is, faintest star you can see is down here at the 6th magnitude. So those are the divisions. 0 would be what they call the 6th magnitude. 6 plus 6 down here would be what they call I'm sorry, I said them backwards. 0 up here would be the first magnitude, okay? And the dimmest star you can see, faintest star you can see at night, would be the 6th magnitude star, okay? There's 5 divisions in between, 1, 2, 3, 4, 5, and the 0 would be the first magnitude, and that would be the 6th magnitude, okay? Now, those are the ones we can see. Now, one of those stars that we think we see, that's not really a star, but neither is it a planet, is actually a galaxy. We can see in about midway out, about 2 to 3 magnitudes out there of brightness, is the Andromeda Galaxy. Not a star, it's a collection of billions of stars, okay? It just happens to be bright enough, and it's the closest major galaxy to us, so we can see it. You can't tell it's a galaxy unless you have a very, very, very powerful telescope. And then you'll see it's a collection of stars. Okay. So that's what we call apparent magnitude, with Sirius being the brightest, and the faintest star we can see out there is the dimmest. Now, notice here, Pluto at its very brightest is so dim you'll never see it with the naked eye. Okay? Even with the best set of binoculars you can buy, you'll never see it. Okay? Pluto's way out there. Now with the large telescope, you can see out to about 19 or 20 apparent magnitudes. Okay? Of course, you can see anything up here, but everything's bled out by the moon. The brightest moon would be about 12 magnitude. The sun is up here about 26 or so. Okay? So that just gives you the range of apparent magnitudes. Now, why they make the brightest thing the negative number and the dimmest thing the positive numbers, I have no clue. Okay? Except they call this first magnitude here is the brightest and 6th magnitude the dimmest. So I guess they started that way. So they had to have positive numbers being dimmer and brighter things being negative numbers. It makes no sense, but that's how they did it. Okay. Now, that doesn't tell us much of anything except how things look. What we're really interested in is really how bright is that star. This would be taking distance, temperatures, size, everything into play here. So this is the brightness adjusted to a defined standard distance. So let's take our sun, that good old average star there. In apparent magnitude, it was down there at minus 26.7. Remember, way at the top. In its absolute magnitude, it would be a plus 4.8. So it's actually past midway what it would be if we put absolute magnitude on that same scale. It would have been down there. Let's just go back to it. It would have been down there right less than the Andromeda Galaxy. It would be right down about here. 4.8, somewhere in there, 4.6. Okay? So our sun drops big time. Now, here's another term. Now, these are just terms. Don't get too fired up about them. Luminosity. In fact, it's about the only time I can remember in the whole chapter they mention this. But it's the total energy radiated into space per second, directly related to the absolute magnitude of the star, not related to apparent magnitude. The units are correlated to the sun. The sun is considered to be one solar luminosity when it's about 4.8. So the very brightest star out there, say +1, or maybe 0 if you called it 0, it would be many more solar luminosities. Then Pluto down there would be a small fraction of a solar luminosity. But don't sweat it. We're not going to use it. Actually, the book is going to use it. We're not. But hang on to the concept. Absolute magnitude. Now, jump another rabbit here. Okay? That's what my mom's...
We can't hear you.
Okay. That was an old saying. My mom said her great aunt or someone used to tell her mother when her mother got to going too long of the story. she say, Nori, let's just jump another rabbit, okay? So we're going to jump another rabbit and go to a different thing. But before we go there, I just wanted to point out to you example 4.2. The brightest star in the Earth's night sky is Sirius. We saw that earlier. Sirius has an absolute magnitude of only plus 1.4. So it is much brighter than our sun. Let me go back a slide. Our sun was plus 4.8. Yuck, I just knocked out my yuck. I'll have to find it later. My flash drive is not in good shape. It just popped out. So I'll have to put it back in before I close things down, but that's why I wanted to find it before it got too dark. Okay, so let me read on. Sirius is about 1.4, which tells us Sirius gives off more light than our sun. How many times brighter is Sirius than our sun? Well, that's the ratio of 4.8 to 1.4. So if you did the math, and I think I have my phone here, so let me see what that is. Well, I could do it that way. Can't do it that way. 4.8 divided by 1.4. That's about 3 times brighter than the sun, though I probably didn't do quite right. Let's see how they did theirs. Actually, it's using a formula we don't have, okay? It's probably not worth going into. If you get to your book and look at it, it's using bases and exponents, and the brightness is the exponent part. It winds up being 23 times brighter than our sun. 23 times. If they were spaced the same distance away, then our sun would be minuscule. It would be very, very bright. They give another example here. Star A and star B have the same distance from the Earth. Star A has a magnitude of -1 and is 100 times brighter than star B. What would be the absolute magnitude of star B? It's less bright. And again, you use that formula that we don't have. They did give it in the book. I'm sorry. The formula is given in the book, but nowhere else is it used. And okay, this is going to be a pain in the neck, but I'm going to do it again. I'm going to share the whiteboard again with you. Okay, and let's do another text box. Okay, here's the formula. You don't need to know this. Okay, but it's this is why I was 2.51 raised to, and again, I can't do that, so I have to use the caret key, raised to the power x, where x is the difference in magnitude between the two objects. That's equal to the ratio of the brightness. And I can't really do this for well. I'll call it B2 divided by B1. That's what I should have been dividing, not the magnitudes. The difference here, this is where the x went, the difference between 4.8 and 1.4. That went there. Raise that to that power, and that gives you the ratio here. So that's where, but don't sweat it. You'll never need to use this formula. But this just gives you an idea of how they go about calculating those things. Okay, so let's leave this and go back to my PowerPoint. There it is. Last time it wouldn't come up, this time it did. Okay. Now, so jumping another rabbit, we talked about absolute magnitude, brightness of stars in absolute magnitude. Now we're going to go to star temperature. Now, how we can measure star temperature, there probably are some physical ways to measure it, but we don't ever get close enough to tell, okay? So we go by colors. Now, which color do you think is the hottest color? Red, yellow, blue, or white?
The brightest color?
The hottest. Which do you think is hottest? Red, yellow, blue, or white?
Yellow?
No, actually blue. Our sun is yellow. There are stars out that are bluish. Now, do you happen to have, as a stovetop, gas, or do you have electric? Your stovetop in your kitchen.
Electric, but I have had gas.
You have had gas. And you know what color those gas lights are? Blue.
Blue.
Those are really, really hot. That burns very, very hot. Not nearly as hot as these stars are, but we use that same pattern. If that flickers a little bit here and there, you'll see little red and yellows coming out of it. They're cooler temperatures. The hottest is your bluish white. Actually, blue is hotter than white. Our sun is an average yellow, okay? That's why it looks yellow in the sky. The color is related to the surface temperature of that star. This has nothing to do with the core of the star, it's the surface temperature. That's what we're looking at. Now, they jump into something called black body radiation curves. And we'll see an illustration of that, and I guess let's go to it now. I think that's what's, yeah, here's what we call black body radiation curves. If, and by the way, the highest, this is stuff they figure you already knew. The longer the wavelength, the lower the energy, okay? The shorter the wavelength, the higher the energy, because wavelength and frequency are inversely proportional to each other, so the higher frequency is the higher energy, that's the shorter wavelength. Now, even very hot very cold stars have some very short wavelength. They have some high energy, but their average is somewhere in here, okay? That happens to be in the orange to red range. That would be a surface temperature of about 3,000 K. That's much cooler than our sun. Our sun is up here. Remember, we're 5,800 K, wasn't it? I believe that's about right. We're in the upper part of the yellow range. 6,000 is just into the greenish range. But the really hot stars, they're up here in the violet range, okay? That's the blue stars, okay? The whites are going to be somewhere in here. The reds are somewhere in here. The yellows in there, okay? So this is why the hottest stars are the bluish stars, those in the upper end of the range. Now, this is what we call the visible spectrum, okay? Okay? If you remember the good old whatever you call it, it's, okay, red, orange, yellow, green, blue, indigo, something in between, violet. Roy, G, Biv, okay? Red, orange, yellow, that's Roy, G for the middle initial of that, blue, indigo, violet. Indigo really isn't much of a color. They just needed a vowel in there, so they called it indigo. It's in between blue and violet, okay? So, the hottest stars, the highest energy stars are your violet, the blue, the violet stars. Your coolest ones are in the red range. Our sun's right smack in the middle, near the middle with the yellows. Okay? So, these are your black body radiation curves showing what we're talking about. Sure, our sun's producing some very intense radiation, but the hotter stars produce even more. Our sun's producing some low-level radiation, but the cooler stars produce less, you know, and it just goes down the scale here, okay? Now, here's how we classify those temperatures, that color scheme. based on the hottest temperature, hottest to coolest. The hottest stars are the O stars. Those are very, very, very short-lived stars. They burn up their hydrogen in literally very few millions of years. Very rare. You don't usually see them. Mostly they're exploding when you see them. The B's are extremely hot. The A's are still quite hot. Now the F's are getting into the white range there. And finally we're into the yellow range with G. That's where we live, in G. Then the cooler stars, sort of the oranger stars, are K, and the redder stars are M. This goes by temperature, okay? The O's, you don't usually see too many of them. B's and A's are very hot, very, very hot. The F's on the hot side of things, G right in the middle, K and M. You don't need to memorize these letters. The thing to remember about them, we're a G. G right in the middle, okay? Now, here's how those work. The O's are bluish stars, very, very hot, temperature range. Now, this is surface temperature, 30,000 to 80,000 K. That's incredibly hot, okay? Now, they tell you a little bit about them, very short-lived and very rare stars to be that big, and they don't last very long, maybe only a million year or two, okay? But they're so hot, they don't have any hydrogen or helium except ionized. This is on the surface, okay? It's so hot that's ionized. The blue stars, the B stars, the bluish stars, 10,000 to 30,000 K, their spectrum is neutral helium, none of it ionized. That's on the surface. In the core, it's ionized, okay? The A stars are bluish on their surface, and they're 7,500 to 10,000 K. Spectrum with no helium, strongest hydrogen. I don't know any reason for that. Begin picking up a little bit magnesium, calcium. Why? I don't know. The F are white stars, like I said, in between. Not as hot as the blue, but hotter than yellow. These are in the 6,000 to 7,500 range. These are the spectrum with the ionized calcium, magnesium, neutral atoms of iron. Don't worry about this part over here. I can't make a lot of sense about it, except they're making bigger and bigger atoms, okay? Your yellow stars, the G stars, that's where we live. 5,000, 6,000 K, we're at 5,600, wasn't it? Or was it 4,800? Somewhere in that range. But anyway, the spectral type of the sun, the spectrum shows 67 elements in the sun. Guess how many common elements we have here on Earth? Just around 67. The ones at the top here, down through here, these down here, we hardly have any on the Earth. And that goes through, if I can keep talking toward the microphone here, 67 goes through holmium, which I'm not even at all familiar with. But that includes most of the things we know. Actually, gold is beyond that, mercury is beyond that, platinum is beyond that. That's what makes them so valuable. We have some of those here, we just don't have great quantities of them, okay? So, we do have some beyond that, but not in large quantities, okay? Then the K stars are your orange-red stars, and those are 3,500 to 5,000 K. You don't need to know these temperatures or anything. Know that we're a G, and just to remind ourselves, our temperature is, what's your temperature? About 5,800 K. Well, that's what I remember. Almost at the edge of the yellow range, but 5,800 K. Okay? Okay. So don't try to memorize anything in this. You don't need it. Just know that we're yellow in the middle, G. Yuck. Why? It went way up here. Oh, am I going the wrong direction? No? No, I'm going the wrong direction. Okay, here we go. Sorry. all you need to know on this one is we're G, we're in the middle, yellow, 5,800. You don't need to know it precisely, but in the 5,000, 6,000, that's our surface temperature, the average old sun that we're in. Okay? Now, finally, we get to tie these things together, and finally, we're almost out of time. So let me start this slide. We'll pick up with this one next time. Okay? Why we messed around with absolute magnitude, remember we did that several slides back? That's one of the scales here. What the absolute, the brightness of the sun or the star is. Okay? We also talked about spectral type. That had to do with temperatures. And the O's were the very hottest stars, the B's hot, A's hot, F sort of hot, G right in the middle, K cooler, M and M8 some of the coolest. Here are the temperatures up here, just like we saw. 3,000 is about the coolest of the surface temperature, not quite. Some will be, yuck, less than that. We're right in the middle, 5,800, right around here. Somewhere right in there. And the hottest stars way up here, 40,000 Ks, 80,000 Ks, somewhere up there. Very, very hot stars. There aren't many of them. Well, why are we messing with all this? When you put this together, and a couple of guys did it, a guy named Hertzsprung and Russell. They put together this diagram. Now, this isn't where they show up in the sky. This is nothing but measuring stars and how they relate to the Earth and other things. Okay? They found that the vast majority of stars, I can't get my cursor back, show up in this middle range here. These are called the main sequence stars. Some of them are very small, very cool, very dim. Some of them are very hot, very bright, very large. Okay? But these are all main sequence stars. They're in the middle of their lifetime. Okay? Now, we're going to get to this later, but once they start messing up, exploding, going away, some of them become what they call the giants. Sometimes you'll read this as the red giants. And then some of the very biggest ones become the supergiants. And see, they can get quite hot over here. Huge stars, okay? The red ones are on the cooler side of things, okay? And then ultimately, some of these stars, their end stage, they will become white dwarfs. And remember I said that center of that planetary nebula was a white dwarf, more than likely. Okay? We're probably close to out of time. Yes, we are. Let me just point. We'll come back to this next time. This is where we'll start. Here we are, right stuck in the middle with you. Okay? Right around a 4.8 magnitude, right in the middle. Temperature, G, right in the middle, 5,800 K, right in the middle. There's the sun. Main sequence stars. Okay? We'll come back to this, talk about the Hertzsprung Russell diagram some more, and then go into the lifetime of a star, which is where we started a long time ago, how it got started. Then we'll see how it ends. Good deal. Any questions, folks? So next time we'll start with class, have class for about 2 hours and 15 minutes, and then we'll move into a lab, and I'll try to have a lab ready for you. If I have something ready, I may send it out the day before. I'm going to try to work on that this weekend. Okay?
Okay.
All right, good deal. Any questions?
Nope.
Okay, I'm going to stop the sharing. Okay, I'm going to end the meeting. So take care. We'll see you next time. That'll be Monday. Two classes next week. Okay, and I will stop the recording.